Take me back from the battlefield. I'm feeling so ill, you don't know what it means. A war is raging just inside my head. I feel so sorry, I feel so sorry I could cry. Soldiers lying sad around me were once companions, now are crushed or empty. Sometimes it feels I can't open my eyes. That way I can see, that way I can see if I die. Take me back from the battlefield. Take me back from the battlefield. Overreacted to an understatement. The night is young, but my liver isn't. Maybe I could reach out and take hold of your hand. Then you could save me. Then you could save me if you try. To spend more time with my lover, and he must spend more time with me. No fun games to play and discover, but I'd rather wait for dusk to come and cover me. This time very special. There might not be another chance. We're gonna be dancing on a tightrope with good hope that love will be the master plan. This night is nowhere to be ended, just like a melody with many words. It has to get printed on a soft heart. It has to play those major chords. with many words. It has to get pretty on a soft heart. It has to play those major chords.
Hi there, in this course we're going to look at vector calculus. In particular, we're going to look at divergence, gradient and curl of vector fields. We're also going to look at the divergence theorem and Stoke's theorem. And we're going to introduce all of these concepts via electromagnetics, and we're going to see how we can use them in electromagnetics. But it isn't actually a course on electromagnetics, but there is some of it in it, but it is described as we go along. So I hope you enjoy the course. I hope it's of use. Everything gets derived. We will be deriving all the divergence, gradient and curl in cartesian, cylindrical and spherical coordinates. And there's a lot of extra added value in the course as well. So I hope you enjoy it and I hope it's of value to you. Okay, goodbye. So let's get started. Now this is a course on vector calculus, so we're going to have a wee look and see what we mean by a vector function. So I've drawn out an axis system here, so we've got our z, our y and our x. Now in a vector function, every single point in space is associated with a vector, so I've drawn out little points in pink here, and each of these points has a vector associated with it. So a vector's got a direction and it's also got a length. Now the best example for this is to think about water flowing in a river. If you were to drop something into the water, say any of these little pink points, then it'll move in a direction given by the blue line, and the velocity will be given by the length of that line. Now the way we draw out vectors or represent vectors is in terms of a scalar coefficient and a unit vector. So the unit vectors here are I in the x direction, so a unit vector just means a vector in this direction of length 1. So we've got I in the x direction, j in the y direction, and k in the z direction, and we build up vectors by multiplying each of these unit vectors by a scalar value in that, and that's how we build up a vector. Now it's best seen by an example. So if we were to write out a general equation for a vector function, we could say the vector function is a function of x, y and z such that it's got a scalar value f in the x direction times the unit vector I, and it's a function of x, y and z, and it's got a scalar in the y direction times the unit vector j, and it's a function of x, y, z, and it's also got a scalar in the z direction times the unit vector k, and it's a function of x, y and z. Okay, so again we'll look at an example and it will become quite apparent. So here's the example here. We've got a vector function of x and y such that it equals minus y in the I direction plus j in the x direction, and it's divided by this value here, x squared plus y squared. So I've tried to draw that out by hand, so we've got a y and an x. Now I've only done this in terms of a two-dimensional vector, so we've only got a vector in terms of x and y. So if we were to try to draw it 3 dimensions in terms of z as well, it would all just get a bit messy. So we can see the unit vectors in the direction I and the direction j here. So if I was to take a point, say at 1, 0, so we come along 1 and we go up 0, so it's just that point on the x-axis, then we can see that the x value is 1, so that means that x value is 1, so we're going to have 1 in the j direction, and the y value is 0, so we'll have 0 in the I direction. So we're going to have just a vector that's pointing in this direction, and the length of the vector again is going to be given by the x squared, which is just 1 squared plus 0 squared, so it's just 1 here in the bottom line. So it's just a vector in this direction of length 1, and as we move further and further out, the same thing happens. The only difference is that the height gets scaled by this factor here, the 1 upon x squared plus y squared. And if you were to do that for every single point along in this plane, then we would create a vector field, and this would be the vector field you see here. Now I've drawn the same thing out in Matlab, so that's it done in Matlab, and that's a function there exactly the same as the function we've got up there, and you can see that we have each of the vectors, and you can see them getting smaller and smaller as we move further away from the axis. Now I've put an M file there called vector underscore function so that you can have access to it and you can draw out your own vector functions, so it's good to draw them out. I've also did it in 3D so you can see the direct vectors and you can draw them out in terms of an X, Y and a Z component. So let's have a wee look at it in MATLAB. Let's just bring this up. So here's a function here, so it's called vector underscore function, so that's available to you in the resources section, so you can just get in and download that. So let's have a wee go of it just now. Right, so we'll run that and you'll see it asks for the I component of the vector field. So I've already drawn these out, so rather than me typing it in again, I'll just connect it here. Okay, so that there is the I component of the vector, and then you can put in the j component of the vector, and in this case here we'll just make z equal to 0. So that's going to draw out your vector here in 3 dimensions, and you can see whenever you bring that down that you're going to get this same vector field that we've seen. Okay, so you can use that code in order to go and generate whatever vector field you want, and I would suggest you go and try that out and get a feel for it. Now just to quickly run through the code, it prompts the user for an input for the I, the j and the k direction. It saves that input in a variable called x in, y in and z in. We then generate a mesh grid for the values x, y and z. I set that up there, these 3 lines, in order to ensure that we don't have any division by 0 problems. And these lines here, they change this symbolic function that you put in into an actual function that we can use in order to generate the values in the mesh grid. And we produce from that a quiver plot, and that's a 3-dimensional quiver plot, and all the rest of the lines there are just to formatting the figure and the output. Okay, so that's all there is to that. Now I hope that's of use. Also, what I'm going to do is we're going to go over stuff. I'm going to cover stuff in the dot product and the cross product, but I'm going to just do that in the appendix. Okay, so if you haven't seen some of that basic stuff, then you can have a look in the appendix of the course notes, and I'll go through derivations of the dot and cross products. So that's all there is to this video. It was hopefully a nice and easy introduction, and I'll get you on the next video. Okay, goodbye. Now, this is a course on vector calculus, but I was going to introduce it in terms of the electromagnetics, because a lot of the stuff in vector calculus was either derived directly or was applied to the area of electromagnetics. Now I'll go through, and this video here is really going to be a kind of crash course on electrostatics, and it's just to give us a kind of lead in. It's as we're going to not just do vector calculus as a mathematical thing. We're going to do it and we're going to apply it to the ideas of electromagnetics. So first of all, we're going to have a wee look and we'll see what we're actually talking about. We're actually talking about an electric force. So if you just watched the little video, I made that little video just showing my examples of electric force. Okay, so you can watch that now. So if you rub a comb against your hair and bring it against the water, you'll see it bend in the water. So it's applying a force on that water, some kind of electric force. Okay. and also you can see it whenever it picks up little pieces of paper. So I hope that little video has convinced you that there is actually something happening, something worth looking at. Now, we've seen then that there is such a thing as a force, and we can call it for the moment just an electric force. And by experiment it was shown that this force is not only attractive but can also be repulsive. So I could get different material and put it next to the water. Instead of attracting the water, it would repel it. So Benjamin Franklin, he came up with the idea of the electricity being of two types, either a positive type or a negative type, and this positive and negative would describe the attraction and the repulsion. So he also came up with the idea of a single fluid model, and the idea about this is that all matter has something, so for at the moment we can just call it a fluid, and either it can have a deficit of that fluid or an excess of that fluid. But what is this fluid that we talk about? Well, the fluid that we talk about, we give it a name, we call it the charge. So there's only really three things that we're interested in here as far as the charge is concerned in this course. We know that like charges will repel and unlike charges will attract. So two positive charges will repel, two negative charges will repel, and a positive and a negative charge will attract. And you can work out the force of attraction or repulsion using Coulomb's law, and we've just simply written Coulomb's law out here. So that's really just reading, saying that there's a force here that's the force on 1 due to 2. Now 1 is just the charge Q1 and 2 is the charge Q2. So we're saying the force on Q1 due to Q2 is equal to some constant times the magnitude of the charges Q1 and 2 multiplied together divided by the distance between the two charges squared, and that force is in a direction along the line joining them. So it'll either be a charge which will be in one direction or another direction, but along that line joining them. So let's say, for example, so you can see that R12 there. If we had a charge Q2 and a charge Q1, then we could say if we had an origin there, then the vector from O to Q2 can be written as R2, and the vector from O to Q1 can be written as R1. So that R12 would just be R1 minus R2, which would give us a vector pointing in this direction. You can convince yourself of that, so it's going to be that vector in that direction plus a vector in the negative sense of that direction, so that'll give us a vector in this direction, which is this vector here, R12. Now, there's one other thing that we're interested in, and that's the idea of superposition. So if we were to then bring in, say, another lot of charges, so they're in blue there, a few other charges, then what we can do is we can work out the charge on 1 due to 2, and we can work out, the force on 1 due to 2, we can work out the force on 1 due to this one, and this one, and this one, and then we can add up those forces vectorially, and we can get the final force that Q1 would experience due to these other charges. So Coulomb's law in itself assumes instantaneous interactions at a distance. Now, what do I mean by that? Well, the force that Q1 experiences due to Q2 is dependent on how far they are away. So let's say I moved Q2 further away, then according to Coulomb's law, instantaneously the force will change. But that's not the way nature works. And the Michael Faraday came along and he was doing experiments, and he came up with the idea of an electric field. So what Faraday noted was that a charge will change the space round about the charge, and there's another charge there that changes the space round about that charge. And then what we can do is we can say, well, if we were to have a multitude of charges, so there's the charge there and there, all the blue ones, and we'll notice that we'll have some kind of field lines round about those charges, so the further away you get from the charge, the less force of attraction or repulsion you'll experience, dependent on the inverse square law. So what we can do then is we can use superposition, and we can add up all of these fields, okay, for each individual charge and create one overall field. And then we'll note then that this is not the only distribution of charges that could create that field. You could come up with a variety of different charge distributions, but you would still come up with the same field. So it means that this field then here is really independent of all of these charges. So then what we can do is you can say, well, let's take some unit charge and we can position it at lots of different points in this field. Okay, so you can take this and you can position it lots of different points all over the field, and then you can measure the force on that unit charge. So that's in effect what we've done down here. We've imagined putting a unit charge on each of the points here, and we measure the force on each of those unit charges. Okay, so then it means that the idea of instantaneous interaction at distance has been kind of split into two. We've thought about the charge creating a field, and then another charge coming into that field and experiencing a force. So this charge here that comes into that field, it doesn't matter where these other charges are. Okay, it doesn't care about these other charges. All it experiences is a field, and as I say, lots of different charge distributions could create that same field. So this point here, this point charge, has got no knowledge of the position of any of these. So we could bring a distribution of charges, say that's the pink ones there, into this field, and then we can work out the force on each of the charges is going to be given by the electric field strength, which is just a function of position, times the value of each charge. So electromagnetic theory is derived in terms of electric and magnetic fields, and the effects that these fields have on charges and moving charges or currents. And these moving charges and currents are the actual things that created magnetic fields in the first place. So that concludes the briefest of introductions to electrostatics. Now the reason for going through that really is because a lot of the rest of the work that we're going to do is focused on answering one of the questions. The question being, what is the electric field given some random distribution of charges? So it's really this problem up here. We have the overall electric field given by some random distribution of charges. So I'll get you on the next video. Goodbye. In this video we're going to start looking at the unit normal to some surface. Now before we get started on that, I want to just give you a kind of roadmap of where we're going. What I've written down here is something called Gauss's law, and it tells you that the E is the electrostatic field, and this is a dot product with the normal vector to a surface, and we're taking that surface integral, and the value of that is equal to the charge enclosed within that surface and divided by epsilon naught. Okay, so you won't have seen that before possibly, and we're going to be working through in the next few videos to try and understand this equation, because within this equation we've got a process of finding the solution of the problem, which was how to find the electrostatic field given some random charge distribution. So we've got the electrostatic field here, but we've got it wrapped up inside this thing here, which is actually, this thing here is called a flux, and it's a flux through some sort of surface. Okay, so we will be working towards this over the next few videos, and it doesn't matter if you don't understand that now, we'll soon understand that over the next 3 or 4 videos. So let's start off with looking at the normal to a surface. So what do we mean by the normal to a surface? Well, if we pick some random, just a flat surface, then the normal component will sit either that way, or we can draw it down that way. Okay, so you get an intuitive understanding. It sits at 90 degrees to the surface. So we could write then that in order to find out, we can use the cross product. So let's imagine we had 2 vectors on the surface. So there's a vector there and a vector here. Okay, we call this vector, say, u, and call that vector v. Then by the cross product, we can say that the normal vector is going to equal the vector u. So that's going to give you the normal vector, but what we're looking for is a unit normal. So we're wanting the normal to be of magnitude 1. So all we need to do, in order to get a normal of magnitude 1, we just got to divide out the normal by the magnitude of the normal. Okay, so we could just u cross v, and we divide it out by its own magnitude, u cross v. Well, we don't even need a bracket there, then I've added it in. Then this here is going to give us the unit normal to a surface. Okay, can maybe just pop a wee block around that. I can call that number 1. So what if we don't have this nice flat surface here? Let's say we're going to work with some random surface. So we've got some random surface, so it looks, say, something like that, and we are looking for the normal at some point on that surface. Okay, then what we can do is, again, we can draw 2 vectors, but what we can do is we could pick an x, y and a z plane, and we could look at the vector, we could look at a tangent to that point, say along here, and look at the tangent to that point in this direction here as well. Okay, so by doing so, if I was to draw this out, and let's say we could just give these, let's say that's our, we're going to have an axis here along that way, so it's going to be an x, and the axis up there is going to be y, and the axis up here this way is, say, going to be z. Then we can work out what the actual vectors u and v will be. So there's going to be some vector along here, vector u and the vector v. So we can work out the vectors. We can draw them out separately. So if we draw them out like that, then we can look at the partial derivative of that vector with respect to x. Okay, so we pick that point there. So this point here, let's say it's a point O. So we've got the point O here, and all we're doing is we're taking that cut in, let's say, in the x direction. So it means that this vector here, if I were to take the tangent to the surface in the x direction, you'd have a tangent that would look like that. And remember, this here is going to be your I component there, and you're going to have a k component up here. So we can then say that if we call this vector here u, then we can say that if we come along this distance here and up this distance, then this distance here is going to be the component of this vector here. So it's going to be the component ux of the vector, and it's going to be the height up here. Now the height up here It's just the rate of change of the function at that point times that distance. So the rate of change of the function at that point is going to be partial f by partial x, because y is held constant, times the distance, which is going to be our u of x. So we can write this vector out here then, which is the vector that sits tangent to the surface in the x direction. We can write that out simply as the vector u is going to equal, well, it's going to be the I u of x, because the I is in this direction here, plus it's going to be the kth value, I'll put a little hat over the top of them, times our partial f by partial x times our u of x. Okay, so again, just to so you're sure, we call that equation number 2. So again, it's just a simple geometric meaning. We've got a surface, and we take a point in a surface, and we've drew the tangent out at that point, say in the x direction, and that's given us this vector here, which is our vector u, and then we've split the vector u into its two component parts. So the vector u is going to have a u of x in that x direction, okay, which is going to be I u of x, and it's going to have a factor of u of x in the z direction, which, okay, so it's going to be our k partial f partial x by times u of x. So it's just that height there. Okay. Now we can do the same for the vector v. Now no different now. Vector v is going to be sitting in the y direction. Okay, so this here is going to be our y, and that's here going to be our z. So again, up here we'll have a k, and along there we'll have our unit vector. This time it's going to be j. So the same scenario exists here, and we've got our point here, which is say point O, and we've got our vector here, which is our vector v, and we can split our vector v into its component parts. There's going to be a part vy, and there's going to be a part up here as well, which is the height there. It's going to be the rate of change of the function with respect to y, where x is held constant, times the distance here, which will give us this component of the vector here. So we're going to have partial f by partial y times our v of y, and that's in the kth direction. Okay, so I'll just put the k there. Okay, so it means that we can write out our vector v. Vector v is going to equal our, and I'll just write it out, it's going to be, I'll rewrite it, v is going to be j v of y plus k partial f by partial y times our v of y. So that's going to be our number 3. So I can take 2 and 3, and I can take out the common factor of v of y and u of x in each of those. So you'll be left with the vector u is going to equal u of x I plus k partial f by partial x, and we're going to have our vector v, which is going to equal our v of y j plus partial f by partial y times our k. So that's our two vectors there. We've separated them into their component parts. So in order to find the normal to that, we'll have to take the cross product of these two vectors. So we'll need to find our u cross v. Now the u cross v, we'll write it out in our usual form. We'll see that it's going to be I, j, and k. And in this instance here, our u of x, we're going to have I is going to be 1. There's no j term there, so that's going to be 0. And the kth term is partial f by partial x. Partial f by partial x. Now for the v, well, the v, we're going to have a j, no 0 I components. We're going to have one j component. And for the k, we're going to have partial f by partial y. F by partial y. Okay, so we've got to take the cross product there. Now, when you take the cross product, of course, we're going to have our I times, and we're going to be cross multiplying that. So that 0 times that is 0, and it's going to be minus partial f by partial x. So it's going to be minus I partial f by partial x, and the second term is going to be a minus, okay, and it's going to be the j times, and we're going to multiply these two together, so it's going to be 1 times partial f by partial y, which is your partial f by partial y, and it's going to be 0 times that. Okay, so that's just 0. And then the last term here, you're going to have our plus k. So the plus k is going to be k times, and we're going to be multiplying, cross multiplying that, so that's 1, and that's just 0, so it's just k. Okay, so that's there. It's not the whole story. We've also got to add in our factors of our ux and our vy, so it's going to be our ux and vy. But note that the values of our ux and vy don't really matter. We could set those to 1 if we want. Okay, so we could set that distance there to 1. We could set that distance there to 1 as well. Okay, so that means that we could just get rid of our ux and our vy. So that there, then I'll just actually get rid of them now because we don't really need them. We could just make them 1. So that there, it's going to give us our normal component to a surface at a point. But we're looking for not the normal component, we're looking for the unit normal, so we're going to have to divide that out by the magnitude of the u cross v. So the magnitude u cross v is quite simple. We're just going to have our square root of, well, it's going to be that squared, so it's going to be minus 1 times minus 1, so that's going to be plus, so you're just going to be left with our partial f by partial x squared. Of course, I times I is just going to be minus 1 times 1, which is 1, and you're going to have the same term here. We're going to have our partial f by partial y squared plus our value of, well, it's just k is 1, so it's 1 times 1, so the magnitude of k is just 1. Okay, so that there then gives us our full equation there for our unit normal. Okay, so I'll put a bracket around that. It looks like a bit of a monster, but it's easily applied, and we'll look at a couple of applications just now to give you an indication of how that's going to work. So I think that's equation number, let's just check and see, we'll call that equation number 4. Okay, so right, equation number 4. So that allows us to find the unit normal. So I really should put equals n hat, which is a unit normal. So let's look at a couple of examples of us using that. So example number 1, we could look at the unit normal to the xy surface. So that would mean that if we had that with z, and we called that our y, and we called that our x, and that's z. So we're looking for the unit normal to just the xy plane. Now we know that that's our j, and that's our I, and up here will be our k. So it's obvious that the unit normal is going to point up here, and it's going to be of a value, it should give you the value of k. So we start off with our function z. So our z is a function of x and y such that z is always equal to 0, okay, which gives us this xy plane. So then all we've got to do is we've got to follow the route up here. We've got to find the partial f by partial x and partial f by partial y and put it into that equation. So we can just go ahead and we'll do that. So we can see that obviously our partial f by partial x equals 0 because there's no z component here at all. And we can say our partial f by partial y equals 0 because there's no z component at all. So these are self-evident. So then you can put these into the equation above, and if you put them into the equation above, then you're going to end up with, well, you're going to end up with 0 for that and 0 with that, and just the k left at the top. So you're going to have k upon, and again bottom line here, you're going to have 0 for that and 0 for that, just going to have a root 1. So you're just going to have k upon root 1, which is just equal to k, which is what we were expecting. So k there is the unit normal to the xy plane. So that's the first example done. So let's go and we'll do one more example. Let's have a look. So we're going to take a function z as a function of x and y such that it equals 1 minus x squared minus y squared to the power of a half. So again we've got to find our partial f by partial x, partial f by partial x. So in this case here, by the chain rule, it's going to be a half of what's already in the brackets, 1 minus x squared minus y squared to the minus a half, and then you've got to differentiate what's inside the bracket with respect to x. The others just look like constants, so that's just going to be all times minus 2x. So the 2 and the half cancel out, and then you can take this whole thing down in the bottom line, it becomes plus a half, so you're going to end up with minus x upon, well, this whole term here is the same as this term here, which is just your z. Okay, so that's the first part of it. Then we've got to look at partial f by our partial y, and by the same principle we differentiate this again but with respect to y, so we're just going to end up with the same as here, that will be minus y, so by minus y upon z. So you just go through that same differentiation again and you'll see that you're going to get that value there. So then what we've got to do is we've got to stick these two equations back into our original equation there. So we're going to end up with the unit normal, and I'll just write the whole thing out here. Unit normal is going to equal our, well, it's going to be the minus I times minus x upon z, and you're going to have the minus j times the minus y upon z, and you're going to end up with the plus k. And on the bottom line we're going to have the root of minus x upon z all squared plus minus y upon z all squared plus 1, and we can rewrite that if we rewrite that as our negative to negative plus. So obviously we're going to have our I x upon z plus j y upon z plus k all upon the root of, I will just square these out, x squared upon z squared plus y squared upon z squared plus 1, which equals, now we can multiply the top line and the bottom line by z, and we can take the z inside the root sign, so it becomes z squared. So you're going to end up with our I x plus j y plus k z all upon the root of x squared plus y squared plus z squared. So that's just the magnitude of that. So this is going to be equal to our I x plus j y plus kz, and that there will be our unit normal. Okay, so that's a unit normal to a sphere. Okay, so that's all there is for this little section. Now we're going to go on and we're going to have a little look at some other parts of that Gauss's law. So we'll be looking at surface integrals, and we're going to be looking at flux, and that will allow us to understand what Gauss's law is telling us. But it still doesn't tell us how to find the charge distribution, because all that's telling us is what the flux is, and we don't want to work out the flux, we want to work out the actual charge distribution. So again, we'll be going on to that further on, and that's the kind of roadmap we're going to be going down. Okay, so get you on the next video. Okay, goodbye. In this video we're going to look at surface integrals. So imagine we had a ball just sitting in space. So there's a z, x and our y coordinates, and we were to approximate this ball just using a lot of squares. So all of these squares will just sit tangential to the surface of the ball, and you could imagine that as we increased the number of these squares to infinity and made the actual area smaller, then this would approximate this smooth ball. So if the ball also is sitting in some vector space, so every point in this space here has associated with it a vector. So there's a vector there, they're all in pink, and I've also drawn in one of the surfaces here, and we've drawn in the normal to the surface. So at this junction here, at this point where the normal is, well, that will also have a vector associated with it from within this vector space. So I've drawn both of these out here. So we've got our little area here, so we can call our area delta S and L for a subscript for the Lth area element. And we've drawn in a normal here, and we've drawn in the vector for this function f xl, yl and zl. Now we know from what we've done previously when we looked at Gauss's law, what we're going to do is we're going to take the vector function and we're going to find the normal component of the vector function. So it's going to be f dot n. So f is a vector function and it's dependent on x, y and z, and n is the normal, and again it's dependent on the position x, y and z. So we're drawing that up here, and you can see that if you were to take the normal component of the vector here, it's like taking the value of the function f but in the direction of the normal. So we can drop the perpendicular down here, and we're looking at f dot n would be this length here. Okay, so that's the component of the vector f in the direction of the normal n. Now let's imagine we take this f dot n and we multiply it by the area element delta s, and then we sum up all of those area elements from L equals 1 to some value n. And then finally what we can do is we can take the limit as the number of the elements, the area elements, tends to infinity, and the actual area of each element tends towards 0 of our function. So whenever we do that, we're going to be left with is we take the limit process, we're going to end up with the surface integral of the normal component of the vector function by ds, which is our surface integral. Now, one thing to note as well is that by convention you can note that the normal component on a closed surface could point out the way, or it could point in the way, and again by convention we decide that the normal component will point outwards from the surface that encloses a particular volume. So let's look at a simpler surface integral. Rather than looking at a vector function, we're going to look at a scalar function here of x, y and z. So let's consider that we have mass per unit area was given by sigma x, y and z. So the mass per unit area is dependent on the position. Then we could find the total mass by multiplying the mass per unit area times the small unit area delta SL and summing those from L equals 1 to n. And again, if we were to take the limit as the number of elements, the area elements tends to infinity, and the actual area of each element tends towards 0 over delta over sigma delta S, then we're going to get the surface integral of sigma xyz by ds, which would give us the mass of a surface. Now let's move on. Now we're going to look at a neat way of evaluating surface integrals. So let's say, for instance, we've got our x, y and z plane, and we've got some simple function, so z is a function of x and y, which gives a surface here. Now let's consider we take a small part of that surface, we just call that part of the surface delta S. Then we can project that surface down onto the xy plane, and that will give us another surface here, delta R, which of course is not really a surface, it's just going to be an area element within this plane xy. Now we're going to ask the question, how can we relate this surface area here to this surface area delta S to this area delta R? Now the way you can kind of think about this is that if you look down from above, then and say shine a light down on the surface, then what we're going to be looking at here is the shadow of this surface. Now you can see that these two are going to be different. So let's take an example of, say, a map. If you have a map of the UK, and if you look at that map of the UK, then you can work out the area of the UK from that map. But that area there would be this area delta R. That area would be different from the actual surface area, because whenever you come down onto the surface of the planet and you are walking about in the UK, you'll notice that it's hilly and the mountains will create an extra area, when that area would be our delta S. So let's look at how we can work out the area, the relationship between our delta S and our delta R. So what we're looking for is a relationship between S and R, so that we can relate the surface integral to just an ordinary double integral over some region R. So again, let's take our X, Y and our Z coordinates, and let's draw out a surface here. So you can see these yellow lines here. I've just drawn out one particular surface, and we say that that area of that surface is going to be the length there, A, divided by that length, the breadth there, B. So the area delta SL is just going to be A times B. But if we were to look down, and that's meant to be like a little eye looking down, so if we were to look straight down, then what we would see would be this area here. So this would be the projected area onto the XY plane. So that area then would be A, which remains the same, but it would be length B dash. So that's this length here. And you can see this length B dash is shorter than our length B. So what we want to do is we want to relate the area AB, which is this area up here, to the AB dash, which is relating the area delta SL to delta RL. Now we can use a bit of simple trigonometry, because we can see that the B dash, which is this length, divided by B is just the cos of this angle, theta. And that angle there is just the angle that the plane makes with the x-axis. So then we can rewrite that as B equals B dash upon cos theta, and then if we multiply both ends by the A, then we've got a relationship between these two areas. So it's going to be AB is going to be AB dash upon cos theta. Now here's another neat little trick which I think is quite nice. If we were to draw the normal component to this surface here, and then we were to draw the component in the Z direction, which is the K component, then this angle here would be the same as this angle here, and we can get that angle by taking the dot product n dot k. Now you can convince yourself of that, because if you were to think this angle here is tending towards 0, so this surface here just tends to get flatter and flatter, then you could see that when it's completely flat, as in it's sitting in the xy plane, that means that this normal component will sit along the same axis as this k component. And then if you were to start moving it up, you'll see that the normal component will start moving along with this angle. So you can see that this angle here will be the same as that angle. And again, if you're unsure about dot product, then you can go and check it out in the snippet section. So we can now replace the cos theta with the n dot k. So then we're able to write that AB is going to equal AB dash upon n dot k. So that means that we can rewrite our area, delta SL is going to be equal delta RL upon the n dot k. So let's rewrite this out in full. If we had some scalar function g of x, y, z, and it's a scalar function that we're finding the surface integral over some surface, then we can write that then as the sum from the L elements from 1 to n of the scalar function times delta RL upon n dot k. And then if we take the limit as the n tends to infinity, that is the number of these little surfaces tends to infinity and the area of the surface tends towards 0, sorry, that's looking at this surface here, tends towards 0, then this is going to give us the double integral of over the region R of our function, our scalar function, divided by n dot k times dx by dy. But we're looking to find just a double integral, but we've got a function here of x, y and z. Now we don't want a function of x, y and z, we only want a functions of x and y because we're going to be different. We're going to be integrating with respect to x and y. But we know that z is just a function of x and y, so you can actually write z as a function of x and y. And you can do the same down here for the normal component where z is still going to be a function of x and y. So now we've got to this point here, but we know that this n dot k, well, we know that the normal vector n from the last video, we derived the normal vector and it can be written as minus I partial f by partial x minus j partial f by partial y plus k upon the root of 1 plus partial f by partial x squared plus partial f by partial y squared. So we're taking this here, which is a normal component, and we're taking the dot product with the component vector k. Then we can see that the I dot k is going to be 0 and the j dot k is going to be 0 and the k dot k will give us a value of 1. So it's just this, we're left with this here. So now we can put this here in for n dot k. But of course n dot k is in the bottom line, so it means that the 1 over, this will head up onto the top line. So finally we're going to be left with this equation here. So we've got original surface integral over scalar function. Now that's equal to the double integral over some region over same function x, y, f of x, y times this value here, the root of 1 plus partial f by partial x squared plus partial f by partial y squared plus 1 dx dy. So this part here is a surface integral over some surface S, and that is equivalent to a double integral over some region R. Now here's a little example. Let's say we're looking for the surface integral of some function z squared, and we say the surface we're looking at for it is x squared plus y squared plus z squared equals 1. Now that surface is going to be the surface of a sphere. Now let's take the projection of that sphere down on the xy plane. So we're looking down here and it's a quarter of a sphere, and we're taking it, looking at down onto the xy plane here. And we can then write z as a function of x and y, so we're just rearranging this such that it equals the positive root of 1 minus x squared minus y squared. So now what we can do is we can take the partial f by partial x, and I've derived that there, it's minus x upon z, and the partial f by partial y by a similar method is minus y upon z. So we can put these in for these values up here, and we end up with our root of 1 plus x squared upon z squared plus y squared upon z squared. Okay, so that then is going to equal our value 1 upon z. So let's continue this on the next page. So we can then write the surface integral z squared is the same as the double integral over the region of z squared times 1 upon z dx dy, which is equal to the double integral of r over region R of the root of 1 minus x squared minus y squared dx dy. So this here is an easier integral to deal with, so we can work through this integral in order to get a value for the surface integral here. Now we're almost there. We've worked out how we can evaluate the surface integral. So what we can do is we can just replace our function g of x, y, z with our scalar function f and with the dot product n, so it's f dot n. Now we want to look at this surface integral in terms of a double integral over some region. So we'll just rewrite it out as previously. We're going to have some function, this vector function f, and it's the dot product of vector function x, f, in the normal direction, and we're taking the surface integral of that. So that's going to be equal to the double integral over some region of f dot n times the root of 1 plus partial f of partial x squared partial f of partial y squared dx dy. So we've seen that just in the previous page. But now we know that the normal component can be written in this form as derived in the previous video. So now what we can do is we can take this here and we can replace the n with this here. But then what happens is all of this here cancels with all of this here. And then what we're going to be left with is the double integral over some region. And if we take these components here, so there's going to be the component of our function in the x direction, so it's minus the component of the function in the x direction times partial f by partial x, and it's going to be minus the component of the function f in the y direction, partial f by partial y, plus the component of our function f in the z direction times dx dy. Now let's look at an example of using this in order to find the surface integral. Let's say we're looking for the surface integral of some function f dot n ds, where the function, the vector function, is given by I of z minus j of y plus k of z, and the surface we're looking to project onto is going to be s equals x plus 2y plus 2z equals 2. So we can then write this function out here, z as a function of x and y, just by swapping the variables around. So we have 1 minus x upon 2 minus y. So then what we can do is we can take the partial f by partial x, which just gives us a half, partial f by partial y, which gives us minus 1. So this integral here, the surface integral, is equivalent to the double integral over a region, and we're just going to have our values here. So we're going to have our value of our minus a half for partial f by partial x up here, and the minus f of x, well, minus f of x in this instance, the minus f in the x direction is just going to be the value z. Well, z is, will be seen as 1 minus x upon 2 minus y, and the same thing for this component here. We've got a partial f by partial y, which is just value minus 1, times our minus f of y. Okay, so the minus cancels with the minus here, makes a plus, and that's just our value of y, so that's the y component. Plus the last section here is just f of z, which f of z from our vector function is just our value x, times dx dy. Now whenever we multiply all this out, you end up with a double integral over some region of 3x upon 4 minus 3y upon 4 plus a half dx dy equals a half, and the dx dy, and whenever you work out that value there, and that value is over some region, and the region it's over, the projecting onto the xy plane, the yx plane, is just gives us this little value here. Okay, so this here is just the projection onto this little area element in here. Okay, so you're projecting that surface down onto that area element. Okay, so that value then in the end, when you work that integral out, is equal to a half. Okay, so that's the last section on the surface integral. It was a longer video. Next video will be a bit shorter, and we're going to go and look at the idea of the flux. Okay, thank you for listening. Goodbye. In this video we're going to look at the idea of flux. Now flux in Latin means flow, so we're going to look at the flow of some liquid through some surface delta S. So if the velocity of the liquid is given by v, then we can see that this distance here is just going to be distance of speed times time. It's just going to be the velocity times the time delta t. Then we can multiply it by delta S. So multiply by delta S, then we're going to get this volume of this cylinder here. So the volume of the cylinder is going to be the velocity times time, that distance, times delta S, which is that area. Now if we think about the fluid as having a certain density ρ, that is a mass per unit volume, then we can say that we can find the total mass if we multiply the mass per unit volume times the volume. So we're going to have our value for our density ρ, the velocity times the time times delta S. Now if we were to go and divide throughout by delta t, then we would have our mass per unit time, which is passing through this surface delta S. So we'll have a mass of water passing through delta S and a time delta t. So this would be the mass flow rate. Now there's one other thing to add to the mix. We know that if the surface that the water is passing through lies perpendicular to the direction, so there's the direction x, and this surface is perpendicular to that direction, then we're going to have the full flow through that surface. If we were to take the surface and we were to turn it around 90 degrees, so it's right now sits parallel to the direction of flow, then the actual flow through that surface is going to be equal to 0. And we could look at lots of different angles between 0 and 90 degrees, and we put an example here of some random angle theta, so we're interested in what that is going to happen to the mass flow rate at some angle theta. So if we were to redraw this out, then we would have our surface here delta S, and if we were to draw the normal to that surface n, and we were to look at the velocity vector v, then we're not interested in the total velocity vector. What we're interested in is the component of the velocity that's in the direction of the normal. Now we can get that by, so what we're interested in is the component of the velocity vector in the direction of the normal. So that's this little component here. That's the velocity vector in the direction of the normal. So if we were then to replace this with our v dot n, we would have our density times our velocity dot n times delta S. This thing here is called the flux. Okay, so the flux is the mass flow rate, but we're not interested necessarily in mass flow rate through this particular surface. We're interested in mass flow rate over some random surface. So what we want to do is form the surface integral by adding up all the flux elements over the entire surface. So we can do that if we note that if we take one particular value here for our density, so we'll take the nth value for example, so you're going to have a density as a function of position, so it's the nth position, and the velocity is a function of position, again the nth position, and the normal is a function of position, the nth position times delta SL, where SL is the area of some small element L. Then if we take the limit as the number of these little areas tend towards infinity and the actual area tends towards 0, then we're going to have the surface integral of the density times the velocity, the dot product of the normal, and that's going to give us the flux, which is the mass flow rate. Now we've seen this before. If we were to replace this rho v with some vector function f, then what we're looking at here then is we're looking at the vector component of f in the direction of n over some surface element s, and that's called the flux. Now we've seen that before whenever we looked at Gauss's law. So in Gauss's law we've seen that the charge in some volume element delta v, so that's the charge of volume of delta v, it's going to be directly proportional to the flux of the electric field over the surface that actually encloses that volume. In this video we're going to introduce the idea of divergence for vector fields. So the original question was, how can we find the electrostatic field given some random charge distribution? And we came up with this equation here, which was Gauss's law, which doesn't tell us the electrostatic field, but it does tell us the flux of the field. So it's the flux over some surface integral S is equal to the charge upon epsilon naught. Now the problem with this is that this is one equation with an infinite number of unknowns, so all the unknowns are the values of the flux over the entire surface. So maybe we can simplify it by, rather than looking at the flux over the entire surface, if we can think about it in terms of the flux at a single point. So now we have to understand what we mean by the flux at a single point and try and get an intuition of what it means for us physically. So if we think about flux in the way we originally derived it in terms of a mass flow rate, then let's imagine we had some little volume of space, that's it drawn out in a little cube, and it's sitting in some vector field, so it could be sitting in some sort of flow, okay, some sort of liquid. And the arrows that are pointing here represent the arrows of the vector function. So what we're interested in is not the length of these arrows, we're interested in the actual normal component to the surface for these arrows. So for example, this arrow here pointing out, we're not interested in this full length, we're only interested in that part of the length, which is the part of that arrow which is normal to this top surface here. So what we're going to do is we're going to add up all of these arrows that are pointing in and pointing out, and we're going to come up with just a single value, it's just a scalar, just a number. Now what's that number going to represent? Well, if you were, say, a little element of a little molecule of water in there, if there was more liquid flowing in here, this little volume element, than flowing out of it, then you would feel some force of compression. If there was more flowing out than flowing in, then it would be the opposite. Okay, it would be, if you like, you could call it maybe expansion. Now, we don't use the word compression expansion, we just use a single term for it and we call it the divergence. So if the divergence is a positive value, then what we say is that there's more water or the more liquid or more whatever you want to call it flowing out than flowing in. And if the value of the divergence is negative, it means that there's more liquid flowing in than flowing out, which means that the field would feel like a compression. So that gives us an intuitive understanding of what we mean by the flux at a single point. Okay, so of course in this instance here the flux isn't actually at a single point, it's over a small volume, but we could imagine taking this volume element and doing the limit as the volume element tends towards 0, we would get the single point in the middle. Okay, so that's what we're going to do now, and we're going to look at that idea mathematically and see whether it works for us. So what I've done out here is the same little volume element, and we've got a delta x, delta y and delta z, and it's in a coordinate system here, so the I is a component in the x, j is a component in the y, and k is a component in the z, and that's a little block sitting, say, somewhere here. Okay, that's the base of it. So we're interested in finding the flux through all of the surfaces. So we take the surface at the front here, S1, and the surface at the back there, S2. We know that the normal component of this surface, S1, points in the positive I direction, and the normal component of this surface at the back points out the way, and it's pointing in the negative I direction. Also, if we look at this surface integral S1 of the normal component of the field here, we can see then that if we draw out just a vector function here, so the function's got a component fx in the I, fy in the j and fz in the k, then when we take the dot product of this vector function here with the normal here, well, the normal is just going to be in the positive I direction, so it's the dot product of this with I, so it's going to be I dot j, that disappear, I dot k, sorry, that disappears, I dot j, that disappears, and I dot I, well that's just going to equal 1, so we're just going to be left with the x component of this vector function. So we've drawn that out here, so that's the x component of this vector function. So we're going to make an approximation to this. So the approximation is that we're going to make is we'll find the point fx, okay, that we work out the vector function f of x at, and we'll multiply that by just the area. So that area of that face there, that area of that face there is just going to be our delta y times our delta z. So we're going to do that. So we're going to work out f of x at, well, the x point is just going to be, we're going to come along here a value of x plus the halfway into this box is just going to be delta x upon 2. So it's x plus delta x upon 2, and y and the z components are just equal to the values of y and z. So if we did the same for the back face, the only difference between this line here and this line is that we're now multiplying by minus I, so we're going to end up with the minus f of x. Now if we add both of these two together, we're going to end up with the equation that we see here. Now what we can do is we can multiply the top line and the bottom line by delta x, so we can get a volume element on the top. So we've got this equation here now. Now what we're interested in doing is we're interested in finding the flux at the point. So what we want to do is we make the volume tend towards 0. So we'll take the limit as the delta v tends towards 0 of this thing up here, which is our delta v, and this thing up here. Okay, so I've just put I've not drawn it out right now again, but these lines here represent this. Okay, so the problem with this is when you take that limit, well, delta v just tends towards 0, so we don't get anything. It's not of any use. So what we have to do is we have to scale the whole thing by a factor of 1 upon delta v. So what we can do is if we divide the whole thing by 1 upon delta v, that means that this limit here, well, that's a very small thing divided by a very small thing, always ends up 1. Okay, so the limit of that thing there is always going to end up the value of 1, and then we'll just have the limit here, so it will tend to an absolute limit. Now, we've seen this kind of thing before, whenever we derived the Fourier transform and we looked at extending the period, and when we extended the period off to infinity, the frequency components tended towards 0, so we had to scale that whole thing by a value in the same way that we're scaling this whole thing here by a value. So it's the same sort of thing. What we can do then is we're interested in taking that limit there. Okay, so obviously when we divide by delta v here, then the delta x, delta y, delta z, that disappears, so this just pops down to the other end of the equation, which is 1 upon delta v. And when we take that limit there, well, this here, that's nothing other than just the partial f, okay, in the x direction. So it says partial f of x by partial x. If you look at it up there, that's all we've got here. It's just that simple partial derivative. And then what we can do is we can do it for not only those two faces, we can do it for the other 4 faces, and we're going to end up with just the partial fy by partial y and the partial fz by partial z. So if we add all of these up together, this will give us the divergence through the entire surface, okay, or actually the divergence of the surface as it tends towards 0, so we'll get the divergence at a point. So we'll have partial fx by partial x plus partial fy by partial partial fz by partial z, and that is called the divergence of the field. And if you like, we can think of that as the mass flow rate per unit volume as the unit volume tends towards 0. And if it's a positive value, it means that there's more flowing out than flowing in. Okay, so we could say that then as a source. I'll write that properly. We could say that point there would be called a source, and if it's negative, then it means that there's more flowing in than out, and we would call that a sink. Okay, so almost done. So what we started off with was one equation and an infinite number of unknowns. Now we've ended up with one equation and 3 unknowns, so we still can't solve for the electric field quite yet, but the solution will come up in the next couple of videos. But we're well on our way to solving this little problem. Goodbye.
In this video we're going to derive the divergence in cylindrical coordinates. Now you'll see that I've drawn a little section of a cylinder here, so we've got our x, our y and our z axes. Now in cylindrical coordinates there's only going to be replaced with z, which remains the same, and a distance r and an angle of theta. So you can see then that this little volume element here we have of the cylinder is going to be given by our distance delta r times the height here, delta z, times the distance round in this arc. Well, the distance of the arc is going to be given by r delta theta. So it means that the volume element here is going to be given by delta r, delta z, r delta theta. Now what we're interested in is the flux through all the 6 surfaces of this little section of a cylinder. Now the flux is going to be given by the surface integral of the normal component of a field. So let's rewrite this out again. So I've drawn it out again. What we're interested in is the front surface here, surface 1, and the back surface here, surface 2. Okay, so that's the front surface, the curved surface at the front here of this, and the curved surface at the back side of it. So you've noticed that the normal components are facing in the opposite directions. So whenever we take the vector function and we form the dot product with that vector function with the normal component, then the other 2 components, there's only one component left at the end, so they're only being left with our component of our function in the r direction, because the dot products with the components in the z direction and in the theta direction are going to disappear. Okay, so because you'll just have, for example, I dot I, which will remain, which would be a f of r, and the I dot j would give us a 0, and an I dot k would give us 0. Okay, so only one component left. So write that component out then as the surface integral of the fr component of a function by ds for area element 1. Now, in order to work out this surface integral, we can approximate it by looking at the value of the function on this front surface in the n direction and multiply it by the area of the surface. Excuse me. So what we'll have then is the point at the front here. Well, the point at the front is given by our function f of r at the front surface. Now the front surface is going to be given by r plus delta r upon 2, and you can see that up here because our r actually comes to the centre of this little section here, and then we're adding on a delta r upon 2 in order to get to the front face, and the theta and z will remain the same. So that's just telling us the position of the value of the function f of r. Okay, so that gives us the value of the function at that point there. Now we've got to multiply that by the area of the face. So the area of the face, well, it's just going to be the height delta z times the distance round in the arc. Now that distance round an arc is going to be r delta theta, but remember that r we're looking at is the r for the front face. So the r for the front face is going to be r plus the value of delta r upon 2. So we're going to have r plus delta r upon 2, delta theta delta z. So that just gives us the area component and the value of the function f of r. Now we do the same for the back face. The only difference in the back face is the normal component points in the opposite direction. So the normal component is going to give us a value of minus fr, and also the back face is going to be given by our distance r minus the delta r upon 2 to get to this point here. And the theta and the z remain the same, and of course the area is going to be the same again. It's going to be our delta theta, delta z, but this time it's going to be the r distance is going to be r minus delta r upon 2, which will take us to this little point here. So now what we can do is we can add both of these together in order to get the flux through surface 1 and 2. So when we add these two together, we take out the common factor of delta theta delta z, we get this little equation here. Now what we can also do is we can multiply this top line of this thing here by r delta r and the bottom line by r delta r. So we do know, so we haven't changed the equation in any way, but you'll notice now that the top line here, r, delta theta, delta z, is actually the volume element here, delta v. So what we can do then is we can form our flux at a single point by taking the limit as delta v tends to 0 of 1 upon v of the surface integral of 1 surface 1 plus 2 of the normal component of the function. And you'll notice then this delta v here, well, that delta v is going to be the top line here. Okay, so it means that whenever we take this limit here, this top line here disappears and we're just going to be left with our 1 upon r delta r. Now when we take this limit here, the delta r, you'll notice, is in the bottom line here with the delta r here and the delta r. So when we take that limit there, we're simply left with the value of our 1 upon r, and it's going to be the partial by partial r of, well, what's left here is the delta r tends to 0, so we're going to have our value of r here. So it's going to be r times the value of our function f of r. Okay, so that means this is the first part of our derivation of the divergence in cylindrical coordinates. Now we're interested also in faces 3 and 4, and we'll go through a similar process with faces 3 and 4. We'll notice that now we're interested in not the variation with respect to r, we're interested in the variation with respect to our angle theta. So if we come back up here, you'll see we're interested in this face here and the other face at the other end here. So what's going to be varying here is our angle theta. So when we rewrite this here, we can see that the only component of the vector function in this direction is the component f of theta. So we're going to have our vector function f of theta, and it's going to be approximately equal to, well, again, we're going to work with the centre of this face times the area of the face. So it's the value of the function at the centre of this face in that direction theta times the area of the face. Now the position is going to be r, but the new position is going to be theta plus delta theta upon 2. Okay, so the theta plus, that's the angle theta, plus the delta theta upon 2 will take us to this point over here. Okay, so it's the far end of this face. So we have to then we'll take out the common factor again of in this case the common factor for the area. Well, the area is going to be delta r times just our delta z. Okay, so that's just this area here, so it's that height times that distance there. Again, you can see that up here. It's just this small area here, which is delta r times the delta z. But we can do the same trick as we did in the previous section here. We can multiply this time by r delta theta upon r delta theta, and it doesn't change this equation at all. And we'll notice now that the top line here is going to be our r delta theta delta z, which again is the volume element. And if we were to take the flux at a point, we're looking at the limit as delta v tends to 0 of the surface integral of the normal component of the field over faces 3 and 4. So this factor here, well, that's just the partial derivative of f of theta. So we're going to have partial f of theta by partial theta, and we're going to be multiplying by, well, the value of r. Of course, the delta theta here just gets subsumed within this partial derivative. So that's going to give us our second component of the cylindrical coordinates. And finally, the third component, we're interested in the value of the normal components in face 5 and face 6. So that's looking at, and back up here, that's looking at the top face here and the bottom face here. So what we're interested in then is the only part of the component of the vector field that's in this direction is the z component. So we're interested in looking at the point in the centre of the face and the value of the function at that point times the area of the face. So we're interested in r, theta and z plus delta z upon 2 minus the same point in the other side of the face, which is going to be minus f of z, r theta z, minus delta z upon 2. Okay, so that's just giving you the value of the function at points 5 and 0.6 above here. And we're going to multiply it by the area. Well, the area is just going to be the r delta theta delta r, and you can see that there. So there is going to be our r delta, it's going to be this distance here times this distance. Now that distance here is going to be delta r, and we're going to have our r delta theta is going to be this little distance in here. Okay, so that's going to give us this area. So what we can do then is we can take this area r delta theta delta r and we can multiply it by, this time now, is delta z upon delta z. Doesn't change the value of the function, but we'll notice the top line now is given as a volume of the small element. So we can go and we can look at the divergence at a point by taking the limit as the volume tends to 0, 1 upon the delta v. So the delta v here is going to be the top line of this function here. So we're just going to be left with our delta z at the bottom. The delta z is going to be coming in here and get subsumed within the partial derivative. So when we take the surface integral of areas 5 and 6 of the vector function and normal component, which is the flux, we're just going to get the partial integral of fz by delta z. So that's the final part of it here. So finally, when we take all of those three and we'll add them together, we get the divergence in cylindrical coordinates. So the divergence of a vector field f, a vector function f, is going to equal 1 upon r partial by partial r of r times f of r plus 1 upon r partial f of theta upon partial theta plus partial f of z upon partial z. So I hope you enjoyed this video. I hope it was of use. In the next video we'll go on and we'll do the same thing, only in cylindrical and spherical coordinates, and it's very similar type of derivation. So thank you for listening and goodbye. In this video we're going to derive the divergence in spherical coordinates. Now in spherical coordinates, the x, y and the z are going to be replaced by an angle of phi, which is an xy plane, an angle of theta, which runs up the outside there of the sphere, and a diameter of r. Now we're interested in this small volume element, so we can see that the small volume element, well, it's going to be given by the distance dr times the length along this distance here and the length up here. So you can see that the length up here, well, that's just going to be given by our radius r times our d theta, but the distance along this distance here, well, you'll notice that along here it would just be given by a value of r d phi, but you'll notice that the value d phi actually changes and it goes towards 0 at the z-axis. So you notice as we head up here, this distance here gets shorter and shorter. So it gets shorter and shorter by a factor of the sine theta. So we'll see that that distance then along there is going to be r sine theta d phi. So you can have a wee look at that and convince yourself of that. So that means the overall volume is going to be given by our dr times our r d theta times our r sine theta d phi, which is given by r squared sine theta d phi dr. Now we're interested in flux through all of the faces of this little element here. So I've redrawn the element out and we're going to look at first of all face 1 and 2. Now face 1 is going to be the top face here, okay, that's facing out, and the face 2 is going to be the bottom face, which faces in towards the centre of the circle. Now you'll notice I've drawn the normals here as well, so the normal is going to face in the opposite directions. So what we're interested in order to find the flux is, we could approximate it by working out what the value of the function is at that point in the direction of the normal, and then multiplying it by the area of the face. So the only component that's in this direction of the normal of that function is the components of the function that are in the r direction. So it's kind of like if you were to find a dot product, and if you were to find I dot I would give us a value of 1, which would give us the r direction, and the I dot j would give us a value of 0, so the phi would disappear, and the I dot k would give us a value of 0, so the function of theta would disappear as well. So I've just written this out then, and I've simplified it, and I've just written the value of the function fr, so that's just the value of the function at that point. Okay, and the point there as well, it's going to be given by the distance r plus delta r upon 2, and you can see that up here. If you see, the distance r is actually the distance to the centre point here, and then plus the delta r upon 2 takes us to the top surface. So we'll have a value of the function f of r at r plus delta r upon 2, comma theta, comma phi, and then we're going to have to multiply it by the area of that front face. Now you can see the area of the front face is going to be this distance here times the distance along here. Now the distance down here, well, that's going to be it would be our r times our d theta, but it's not the value of r, because we've got to get to the front face. It's going to be r plus delta r upon 2 d theta. So that's one of them done here. So I've got r plus delta r upon 2 times our, now I've actually not using the d value, I'm just using the delta, okay. So r plus delta r upon 2 times delta theta, and then we're going to have the same for this distance here. So it would ordinarily be r plus delta r upon 2 times our d phi, but of course we've got to add in our factor of our sine theta there as well. So we're going to have our r plus delta r upon 2 sine theta d phi. So when we put those two together, we're going to have our r plus delta r upon 2 squared, delta phi, delta theta, sine theta. So that's for the flux in the front surface. Now the back surface, it's the same thing again. The only difference is that instead of going forward by delta r upon 2, we're going to go back by delta r upon 2, and also the normal is in the opposite direction, so we're going to have a negative value there. So it's going to be minus f of r minus delta r upon 2 squared, delta phi, delta theta, sine theta. Okay, now we can take that whole thing there, we can do the same trick as in the previous video. We can multiply this whole thing by our r squared delta r upon r squared delta r, and there's no any change in that whenever we go ahead and we do that. But we notice now what we're going to be left with is our value of r squared delta r sine theta delta phi delta theta. So that top line there is now going to be that little volume element there, and that's the reason for multiplying with this, in order to get the volume in the top line. So now, in order to get the flux at a point, what we've got to do is we've got to divide out by that volume element. So we're left with the limit as the volume tends to 0 of 1 upon delta v of the surface integral of the normal component of the surfaces 1 and 2. And you can see then we're going to be left with, well, our delta r is going to get subsumed within this limit here. And when we take that limit there, well, we're going to be left with the partial derivative, so it's going to be partial by partial r of, well, there's going to be an r squared term there because the delta r will tend to 0, so we'll have that r squared term, and we're also going to have the function f of r. And we're going to be left here with the bottom line, the limit there, the delta r will disappear, and we're going to have our 1 upon r squared. So we're going to have this first factor here, 1 upon r squared partial r squared f of r all upon partial r. Now that's face 1 and 2. Now we're going to go and look at face 3 and 4. Now face 3 and 4 are these faces here. So the face that faces up the way here, I'll just get it up a bit. So it faces up the way here. So we're looking in this direction, and face 4 is this one here, this little face looking down in that direction there. So we go through the same process for this one here, and we'll notice that we're now looking at it in terms not of our adding up our small elements delta r. R is going to be fixed. We're interested in looking at it in terms of our delta theta. So you can see there in this instance here, it's these two faces here. So we're interested in the variation with our angle theta. Okay, because those will sweep out that volume in that direction. So we're going to have our value of our function theta at theta plus delta theta upon 2. Of course, we're going to be our r and our phi in there as well, but these are just going to be our fixed values. Okay, so we're going to have that value of our function theta. Again, we only left with the phi component because the normal is in this direction, and in that direction, that's the normal in the direction of phi. Okay, so it means that the theta and the r will just disappear from the function f. Okay, so we've left with that value of the function in this direction, and that's at angle theta plus delta theta upon 2. So we'll go up there and we can see our theta is this point here plus delta theta upon 2. We could say is maybe that the back face there. Okay, and we're interested then also in looking at the area element there. So the area in the bottom element there, well, area bottom element is going to be given by our r sine, and it's going to be theta plus delta theta upon 2 times delta r times our delta phi. And you can convince yourself of that as well if you look at the small element there at the bottom there. Then you can see that that volume element there is going to be given by our dr times this distance here, and we know that distance there because it's going to be our r plus delta r upon 2, the sine of the theta d phi. Okay, so we do the same for the back surface as well. And no difference to the back surfaces, we're going to have our distance there is going to be the distance minus, sorry, but actually at the top here, it's going to be the distance here, plus our delta theta upon 2, and we'll have our minus delta theta upon 2, will take us down to the bottom plate there. So if we were to then take out the common factors here, so the common factor here is going to be for both of these, common factor is going to be r delta r times our delta phi. Now we do the same trick again. We want to try and get a volume element at the top, so to get the volume element we have to multiply by our r sine theta delta theta divided by r sine theta delta theta. Okay, so we're not doing anything different by multiplying out by this line. That equals that would cancel out. But now on the top line here, along here, we're going to have our volume. Okay, so that r delta phi times r sine theta delta phi, that's going to be, delta theta is going to be our volume element. So then, in order to get the flux, again, the flux at a point, we take the limit as the volume tends to 0 of 1 upon the delta v. So 1 upon the delta v is this section up here. Okay, and our delta phi is going to get subsumed here within the partial derivative, and we're just going to be left with our 1 upon r sine theta. And whenever you take the partial derivative, it's going to be partial by partial theta over, well, it's going to be our f of theta times our value of sine theta. Okay, so that's the second part of this derivation. Now the final part, we're going to look at sides 5 and 6. So sides 5 and 6 are these sides here. So I'll come up the top. So it's going to be this side here, okay, and then the opposite side there. So this is going to be sitting in the the variation is going to be within the phi plane, okay, or if you like the xy plane. So let's go ahead and we'll do that. So again, now we're interested in the f of phi, but we're interested at phi plus delta phi upon 2. So we work out the value of the function there, and then we multiply it by the area. Well, the area is simply the r delta theta times our delta r. So you can see that up here. So the area of this point up here is just going to r delta theta times the value of delta r. Okay, so we do the same on the opposite face as well. We're adding phi minus delta phi upon 2, and you'll note we do the same trick here again. In order to get this into the terms of a volume, we're going to have to multiply by our r sine theta delta phi upon r sine theta delta phi. So it means that in order to get the flux at a single point, so the flux at a point, then we're looking at the limit as the delta v tends to 0 of the surface integral of the normal component of our function. So the delta phi is going to be subsumed here within the, whenever we work out whenever we work out the derivation for the partial derivative. So we're going to end up with our 1 upon r sine theta partial f of theta by partial theta. So that's going to give us our values for the surface 5 and 6. So all we've got to do now is add up all of these three. So when we add up all of the three, we'll get the divergence of the function, and spherical coordinates will be 1 upon r squared partial by partial r of r squared f of r plus 1 upon r sine theta partial by partial r sine theta f of theta plus 1 upon sine theta partial f of phi by partial phi. So bit of a long-winded one, some awkward maths, but we'll get there in the end, and I'll get you on the next video. Okay, goodbye. This is a short video just to introduce the idea of the del operator. So the del operator, that's an upside down triangle. So del equals, well, it's the I component partial by partial x plus the j component partial by partial y plus the k component partial by partial z. So if we were to take the del component and we were to dot it with a vector function, then we would have this here, which is above, times the vector function, which would be I f of x plus j f y plus k f of z. So that means that the I would cancel with the j and the k, and the j would cancel with the I and the k would cancel with the I and the j. So you would just be left with the partial f of x by partial x plus partial f of y by partial y plus partial f of z by partial z, which is just the divergence of the vector function f. So we can then write div f in this form here, del dot f. So in terms of the electric field, we've seen that the divergence of the electric field is equal to rho upon epsilon naught. So we can then write the divergence of the vector field del dot E equals rho upon epsilon naught. So I've just repeated that down here. So there is the differential form of Gauss's law, del dot E equals rho upon epsilon naught. That's all there is for this video. In the next video I'm going to go on and we'll have an informal look at the divergence theorem, and that will finish off our videos on divergence. Okay, thank you for listening. In this video we're going to take an informal look at the divergence theorem. So the idea is that if we had some surface here which enclosed a volume, then we could find out the flux through this entire surface. And there's the equation there for our flux, which is the normal component of a vector function over the entire surface, so that's the flux over the entire surface. So then if we were to look inside this volume and we were to split that into small volume elements here, and then we were to look at the flux through each of the volume elements, and then if we were to look at an infinite number of these elements and add up all of the flux, then we've got the equation below. So we're going to have the flux through some surface, okay, say for example that surface there, is the normal component of the vector function f over s. And now if we were to then add up all of these components of the flux, then we would be summing L equals 1 to n. N is the number of faces of this value here of the flux. But then if we were to note that if we stuck two of these volume elements together, then the normal component would be in this direction here at S0, and also this direction there, the opposite direction at S0, where both of those surfaces join together. So we could see that the flux in one direction will cancel the flux in the other direction. So if we add up both of the flux S0, the entire flux is going to be equal to 0. Now if we were to then add up more and more of these surfaces, we'll notice that these volumes, we'll notice that the surfaces where they connect, the flux is going to equal to 0. So it means that if we continue this up until we build up the entire surface, the only flux that's actually going to count would be the flux that actually on the surface of the yellow surface here, okay, which would be the flux over the entire surface. So kind of stated in word, we're really saying that there's a cancellation for all of the adjacent subvolumes, the subvolume surfaces. So all subvolume surfaces are adjacent to two subvolumes except for the outer surface. Okay, so that's really just a statement of what we've seen here, okay, and extended to an infinite number of volumes up here. So that's really in essence what the divergence theorem is. But so let's continue with it. So if we were to write this surface integral here, and then if we were to add up all of the other surface integrals, but we'll multiply by delta v and divide by delta v. So in doing so, we can see the stuff that's in the brackets. That's just the divergence of that field. So then we can write down here that if we were to take this here, and if we were to take the limit as the number of those surfaces tended to infinity and the value of the volume element tended towards 0 of this divergence, then we would just have the triple integral of the divergence. So all we're really saying is that we'd have the divergence at a point, and then if we were to find, we could find the total divergence by adding up the divergence over x, y and z direction, and that total divergence would just be the flux through this surface. Okay, so that in effect is the three-dimensional divergence theorem. So divergence theorems relate, in this instance, surface integrals in 3 dimensions, surface integrals to volume integrals, and there's a related quantity. The quantity here is the divergence of the field, and here it's the flux in the field. So we could really say that the mass flow rate, or the flux through the surface here, is equal to the mass flow rate per unit volume when we sum up the entire volumes. Okay, now that's the divergence in 3 dimensions. You could look at the divergence in 2 dimensions and it would relate surface integrals to line integrals, and then you could look at it in 1 dimension, which would just be the fundamental theorem of calculus, which would relate differentiation and integration. So possible to do another video detailing that stuff in more mathematically precise detail. Okay, so but that's enough for now, and that's the divergence theorem that we're going to be using. So let's look at a couple of applications. So the first application is in terms of the electric field. So we've seen that Gauss's law can be written like this here, and on the right hand side, this is just the total charge upon epsilon naught. So that's the charge per unit volume integrated up over the the entire volume. Okay, so it means that from the divergence theorem we can see that these surface integral can be related to the volume integral by the del operator. So we would have, we can replace this here with our del dot E. So that means that this thing here is going to equal the triple integral of the maximum, the total charge. Okay, so we're going to end up with our triple integral of the del dot E is equal 1 upon epsilon naught triple integral of rho dv. So this can then be rewritten as del dot E equals rho upon epsilon naught. Okay, so that's just another little derivation of the Gauss's law, which we've seen in the previous video using the divergence theorem. So let's look at a second example. This is the continuity equation. So let's say we have some substance, say water, flowing through some volume. So we have the water density, or the density of the material or liquid. So it's a mass per unit volume. And we have some velocity of the substance as well. So that's velocity as a function of x, y, z and t. So we're asking the rate at which the substance and the volume is changing. So the total amount of substance in the volume is the mass per unit volume integrated up over the entire volume. So that's the total amount of stuff. And we're asking what's the rate of change of that stuff with respect to time. So we differentiate that with respect to time and we get this little equation here. So we know the rate of stuff that's flowing through the surface from the idea of divergence is going to be given by the surface integral, and we used this very method in order to derive the surface integral a couple of videos ago. So the rate of change of stuff in the volume is equal to the rate at which it is flowing through the surface. Okay, so that's the rate of change of stuff in the volume, and that's the net flow through the surface, and it's negative because it's a flow into the surface. So all the stuff in the volume must come through the surface. So then we can say by the divergence theorem that this flow through the surface is equal to the entire stuff in the volume. Okay, but this entire stuff in the volume is going to be replaced by del dot rho v via the divergence theorem. So then we can rewrite this out in this form here, and the triple integrals disappear, and we're left with our partial rho by partial t equals minus del dot rho v. So we can rewrite this equation, bring this across. So partial p by partial rho by partial t equals plus delta del dot j equals 0, where this idea j equals rho v is the current density. Now it's quite a quick talk through that. That's called the continuity equation. We'll come get up against that in other places, so whenever we do the full course in electromagnetics we'll see this in more detail.
We're going to look at the divergence of a vector field in Matlab. So I've created an M file which is available to you, and it will be in the resource section of this video, called divergence.m. So in that I've generated a couple of examples. So we'll go to the second example and we'll have a quick chat through it. So we have a vector function here, and its I component is here and the j component is here, and we've plotted out that vector function, and you can see that in the yellow area the arrows are heading outwards, so that is going to be a source. So if you like, in terms of divergence, it's going to be an area of expansion, and in the blue area all the arrows are heading in towards the centre, so if you like, that's going to be an area of compression, or it's going to be a sink. So we said that a source is going to give a positive value for the divergence, and the sink will give you a negative value for the divergence, and you can see that here because the yellow region here has got a positive value here for the divergence, and the blue region has got a negative value there for the divergence. So you see the divergence is just going to be a scalar function of the position. So let's go ahead and we'll have a wee look at it in Matlab. Okay, so this is the function in Matlab called divergence.m. Now we'll just run through this example and then afterwards we'll have a quick look at the program. So when you run it up, it's going to ask you for the I component of the field. So in this instance here we can just call that minus sin x times sin y. And then ask you for the j component, which is going to be cos x times or cos y. So that's generated two figures. So the first one, figure 1, is just the vector field, and the second one is the divergence. So I'll get it so it's sitting in the right angle. Okay, so that's I along there and y along that axis, and again we're going to have our x along that axis and y along that axis. So that's the same as we've seen just in the previous example. Okay, so that's the vector field and that's the divergence. The only difference is that there's no contour map on this one. Okay, so we can see then, as we've seen in the previous example, we've got the area here which is going to be our source, and this area here is going to be our sink. The source are going to give us a positive value for the divergence, and the sink we're going to give us a negative value for the divergence. So let's have a quick look at the code. So it requests the I component and the j component. It places the function in a variable called x in and a function for the j in a variable called y in. It then takes that function, which is a symbolic function, and generates the actual values on a grid and produces a quiver plot, okay, which is really just us producing the vector function, and all the rest of it's just to format the output so as it looks neat and tidy. We then calculate the divergence, so there's only three simple lines there in order to generate the divergence, and then we plot the divergence of the function, and again this is just done with this function here, the surf f, the divergence, and it just puts in the limits, and the rest is just for formatting the actual graph, the actual figure. So that's all there is to this part. Now you can go ahead and use that and have a little try with it, put in a few examples, and it's a good way of understanding the divergence. Now you'll actually get better understanding the divergence whenever we go in and we have a look at the gradient and also the Laplacian, but we haven't introduced those as yet, so I didn't want to introduce those or talk about them at the moment, but it'll all come clear as well why we're doing this whenever you see the gradient and also the Laplacian. One other thing, if you wanted to actually calculate the divergence of a function, you could just use these simple lines here. Okay, so you can put in your field, which is really just the function in terms of the I coordinate, the j coordinate, and also a z coordinate, and then you can just use this simple section here, divergence of the field in the variable x, y, z. And note here, we've only generated the divergence in terms of a two-dimensional vector field. It just makes it simpler for us to see what's going on. Okay, so thank you for listening, and I'll get you on the next video. Okay, bye bye.
In this video we're going to start looking at line integrals. Now, just to recap, the question that we've asked, and it's been a theme throughout the previous videos, is that given some random charge distribution, how can we find the electric field? So we did come up with Gauss's law, which tells us the flux of the field over a surface is equal to the total charge divided by epsilon naught. And then we were able, through the idea of divergence, the divergence theorem, to write that in this form here. So it's the differential form of Gauss's law. So it tells us that del dot E is equal to rho upon epsilon naught. So rho is the charge per unit volume. So we were started off with one equation and an infinite number of unknowns, and we progressed to one equation in three unknowns. But we're still in the process of trying to work out where do we go from this point here with one equation and three unknowns. So that's the direction that we're going to take at the moment, and that's going to introduce us to ideas of line integrals and curl. So first of all, we're going to look at the idea of work. Okay, so in work in physics is defined as the work done is equal to the force times a distance. So if you apply a force to an object, there's a little man here, option 1 here, a little man applies a force F to this object here, and it moves a distance d. So then you could draw down a little graph and you can say, well, there's the distance d, it's moved along the axis here, and that's the force that you've applied. So if we are applying a constant force here, so the force doesn't change, it doesn't wave up and down, it's just a constant force, then we can say the work done is going to be the area under this graph. It's going to be our force times our distance. But as you well know, when you go to push some things, you maybe get a little bit tired and you don't apply the same force all the way through the push. So again, we're pushing it with a force F over a distance, but this time here the force F is variable. So we're still looking at the area under this graph here will give us the work. But the area now, instead of force times distance, is going to be the integral of this function of x times dx, okay, where x is the distance moved. Now, it's not just as simple as that though, because we know that if we were looking at above, say here, and we're applying a force to try and push a car, then if we are applying a force from the side, but the car doesn't move in this direction, it'll move in that direction there. Now the only force that we say that does work is a force that is applied in the direction of the movement of travel. Okay, so that's the direction of movement of travel there. So the only component of this force here that actually does work is a component in that direction. Now the component in that direction, you can see if you say F1 upon F is going to be the cos of this angle. So it means that F1 is equal to F cos this angle theta. Okay, so whenever we write down our force equations, it's not actually force times distance, it's going to be F times d cos theta. So we can write this out again, rather than as f d cos theta, we can write it out as f dot d, so we can use the dot product. Now if you're unsure about the dot product, there's a little video up here, and you can have a little look at that video and that will explain what the dot product is. But that's not going to tell us the whole story, because what if we really generalise it and we have just a three-dimensional space, so it's just an x, y and z coordinates, and you can take the components as an I, j and k. And let's say we push an object and it moves in space, and it moves in just a three-dimensional sense, so that is, imagine that as travelling through space in some random direction. Then the work done, as previously we've seen, if it was a variable force, would be the integral f of x dx, But what if it was a variable force and it was applied and we moved over some variable direction? Well, then what we could look at is, rather than it be F dot d, we'll be looking at it would be the only component of the force that does work would be in the direction of movement. So I've drawn a few spots on this curve here. So the direction of movement at each point is going to be the tangent at that point. So at that point there, the direction of movement is in this direction, and the direction of movement here is in that direction. The direction of movement is there, the direction of movement is up there. So we need to find then the tangential direction, the tangential component for all the points along this surface, so that we can then form, instead of F dot d, it's going to be our force, and it's dotted with the tangential direction, and of course the d is just the ds, which is, the ds now is a small element along this curve. Okay, so that becomes our equation for our work. It's the normal component of the force in the direction of movement over the small surface, small direction element ds. Okay, the magnitude of this small element of curve ds. So that's what we're looking for. But we know that this force, well, we've written out forces before, we've written out functions before that are vector functions, so we can split that up into its component parts. So the component parts are going to have a force in the x direction, which is given by I, which is a function of x, y and z, and the same for y in the j direction, and the same for k and z in the k direction. Okay, so we've seen that before, and we've dealt with that in one of the very first videos. But what we're interested in is finding this value t, which is the unit tangent to this curve. So how do we find that? Well, let's imagine we draw a little section of the curve there in yellow, and we take a couple of points in the curve, say we call that point S, and then we've got another point in the curve here, it's going to be S plus delta S. Okay, so what we do is we imagine the curve as being parameterized with respect to the arc lengths. Okay, so what we're saying is the position of a point on this curve is given by the x component, which will be some function x of s, and y is y of s, and z is z of s. So what we're really saying is that this, if we take this infinitesimal length here s, then this infinitesimal length here s will actually give us the function that will tell us the x coordinate, and the function that will tell us the y coordinate, and the function that will tell us the z coordinate. Okay, so we're parameterizing this curve with respect to its arc length. So then we can say that the point s plus delta s is going to be x of s plus delta s, y of s plus delta s, and z of s plus delta s. So we could draw a little arc joining, so that's just a straight line, so we can draw that little line from s to s plus delta s. We'll call that delta r. So that delta r, that's just a vector sitting in space, so that vector can be written as I delta x plus j delta y plus k delta z. Okay, it's just a simple vector. So then what we can do, and you can see this up here using a wee bit of thought, if we let this value delta s tend towards 0, then that delta r, you can see by simple differentiation, is going to tend towards the tangent at that point. So we'll just do that. So we're looking at delta r upon delta s. Well, delta r is what we have above, divided out by delta s, we have this here. And then if we take the limit as s tends towards 0 of delta r upon delta s, we get this here, I dx by ds plus I dy ds plus k dz by ds. And we can see then that that there is going to be the tangent. But we can note as well is that as delta s tends towards 0, then the magnitude of delta r, so as this delta s tends towards 0, then the length of this delta r, well, it'll tend towards the length of that little arc delta s. So it means that if we take that limit as delta s tends to 0 of delta r upon delta s, well, this one just tends towards that value, so they tend towards the same value. So we're just going to get the limit will tend towards 1, so it's just like dividing two numbers together with the same number, so you'll just get a value of 1. So it means that not only does this equation here give you the tangent, it actually gives you the unit tangent. Okay, so that's us found our unit tangent t. So the unit tangent t can be written as I dx ds plus j dy ds plus k dz ds. So that is our unit tangent. So we can put this here back into our equation up here, and you can see that what you're going to get is, when we put that into that equation up here, we're going to get our f, sorry, I'll come back up again, we're going to get our vector function f, okay, that has got components I, j and k, and we're going to have a vector function t that's got components I, j and k. So of course whenever the I multiplies with the I, we'll get a value of 1, but when the I multiplies with j, we'll get 0, and when the I multiplies with k, we'll get a 0. So we'll only get one component for each of these whenever we multiply them out. So I've not written it out in full, but you can see then if we have our vector function here and we take the dot product of the vector function with this function here, then when we dot the I here with the I in this here, we get a value, but when we dot the I in here with the j, we get a 0. We dot the I with a k in here, we get 0. The same for this, we'll only be left with the j component, and the same with this, we'll only be left with the k component. So we'll simply be left with the function, but only the x component of the function, and the function, the y component of the function, and only the z component of the function, times our dx, times our dy, and times our dz. So that there is the final value that we're looking for, the equation we're looking for, that defines the work done over some path. Okay, so that's the end of really the derivation there, and that's all the derivation. So we'll go on and we'll look at simple examples. This is the example that's straight out of the book, so I'll just talk our way through. So we've got, let's say we've got a closed path here, so we travel along C1 up C2 and down C3. So we've got some vector function there that's defined in this space, and it's a function of x, y and z. It's such that it equals I, y minus jx. So we know we're looking to find the work done in moving round this loop. So the work done, from what we've seen before, is going to be the normal component of this vector function. Sorry, it's going to be the vector function. It's going to be the dot product of that with the tangential component added up over each small element ds. So we can write that as per the bottom of the last page there is the integral of y times, and you can see this now if I go back onto the last page so you can remind you it. So we can see it's going to be f of x dx, f of y dy. Okay, so let's go back in there. So it would be f of x dx. Well, f of x in terms of dx is just our y component. Okay, so that's our y component, that's in the direction of I, okay, which is related to our dx, which is going to be the value of y, and then the f of y dy. Okay, well the f of y component, well the y component is just the factor of minus x here. Okay, so we're going to have a y dx minus x dy. So we get around our three paths, C1, C2 and C3. So we notice in path C1 that, well, the y equals 0 and dy equals 0. So it means when we do this integral, we're going to have our y is 0 there, so that term's 0, and we've got our dy is 0, so that term's 0, the whole thing's 0. And then when you go in and look at path C3, then we know at path C3 our x is equal to 0 and our dx is equal to 0 along that path. So we can see the integral of y and the dx equals 0 there, so that disappears. And this section here, our x equals 0, so that disappears, so that whole thing is equal to 0. So the only thing that adds any work is going to be along path C2, and we got to work out the parametric equations for that path C2, and here they're done here. If we write that point there as 0.1, so we can see a distance along here to that point there is going to be 1 minus x. Okay, that's our x there, that's our y. So it's going to be 1 minus x. So you can see 1 minus x upon s. Okay, so s is the distance up here, is equal to the cos of 45 degrees, which is 1 upon root 2. And you can also say that y upon s, this distance here, is going to be our sine of 45 degrees, which is also 1 upon root 2. So then we can rewrite that as, and transpose that for x. So x is 1 upon s, 1 minus s upon root 2. And if we differentiate that, you just get minus 1 upon root 2. And we can transpose this for y. So y equals s upon root 2. We differentiate it, you get 1 upon root 2. Then what we want to do is we've got to work out our integral up here. So y dx minus x dy. Okay, so we just pop our values in. So we're going to have our value here of s upon root 2 for our y, and our dx is going to be our minus 1 upon root 2 minus the value 1 minus s upon root 2, which is our x, times our dy, which is going to be our 1 upon root 2. So we work that out, and we'll get our, take a common factor, minus 1 upon root 2 out, the integral 0 to root 2, and we get our value, work through that, we'll eventually get our value equaling minus 1. So the work done is minus 1. Okay, and the only direction the work is getting done is in this direction here, so there's no work done in this direction or in this direction, so there's only that one part of the path. So that's all there is for this video. Next video we'll go on and do a little example on path independence, and then we'll move on to the idea of curl. Okay, so thank you for listening and goodbye. In general, when we find line integrals, the value of the integral is going to be path dependent, but there are circumstances where the value of the integral is not path dependent, and one of those you'll see is the electrostatic field. So we'll go and have a little look at that in general, and well, look at that in particular with electrostatic field, then look at it in general. So we had this equation here, Gauss's law for the electrostatic field. So we've got it drawn out here. So we've got our x, y, z coordinates. We have a point here, q, so that's one charge q, and there's our charge q naught. So this equation here gives us the charge experienced by q due to the charge q naught. Okay, so this force is going to be 1 upon 4 pi epsilon naught times the product of the charges q naught, and divided by the distance between them squared. So that's the distance there between them squared, distance r, and it's in a direction given by the u hat. Okay, so that's a component, unit component, and that is in the direction between these two charges. Okay, so it's going to point out in that direction. So what we can do is we can write first of all that our unit component u is going to be the length of, it's going to be r divided by the length of r there. Okay, so the value of r, well, you can write r simply as a vector, so you can write that simply as ix plus jy plus kz, so that's just some vector giving us that position there, and if we divide it by that length of r, we'll get this value here, which is our u hat. So then we can say that our value of our force F in the direction experienced by Q is going to be our Q naught 4 pi epsilon naught, and you can see then that this value u hat is then replaced by this value here. Okay, so we end up with this extra term on the top line, and we end up with an extra r on the bottom line, so the r now squared now becomes our r cubed. Okay, so if we were to look at this here, and we're looking at the force, and we're looking at the dot product with the tangential component, so it's the tangential component of this force times some element ds. Well, I could just put it in as our q naught upon 4 pi epsilon naught, and you can see here that if you were to take this value here for our force, you'll see that we've got I, j and our k, so we dot product that with the tangential component. Well, I know the tangential component has got a component in I dx by ds plus j dy ds plus k dz by ds. So it means that when we look at the I component, well, the I component will multiply that I component there, which will give us 1. So we'll just be left with our x, and the ds's will cancel out. So we just have x ds, and the same thing will happen for our y, and we'll have our j y dy, and the same thing will happen for our z. The k's will multiply, and we'll have our z dz, and the other factors will disappear because our I dot j 0 and I dot k 0, and the j dot k 0 and the j dot I 0, and the k dot j 0 and the k dot I is equal to 0. Okay, so we'll just be left with this equation here. So if you're unsure of that little section there, look at the previous video where I derive this f dot t, okay, and you'll see where that comes from. So what we can note here, and a little trick there that employed really, is that we can see that that distance r is going to be x squared plus y squared plus z squared to the power of a half. Okay, so that's just this distance here. Then we can, if we were to, we can look at the differential form of this, so we can just differentiate this with respect to our r and our x, our y and our z. It's going to give us our implicit differentiation will give us our 2r dr equals 2x dx plus 2y dy plus 2z dz, and you can divide out through the by 2's, and you're just going to be left with the r dr equals x dx plus y dy plus z dz. Okay, so we can say then that this f dot tds is going to equal, it's going to be q naught upon 4 pi epsilon naught, and what we're going to do is we're going to stick this r dr in for this section here up in this equation. So we replace this here with the r dr, so one of the r's is going to cancel out and just be left with 1 upon r squared in the bottom. So you're left with this equation here. Now what we're going to do is, if we were to take 2 points, say in a curve, so we start off at point 1, and then we've got another point 2 here, and if we were to do this integral along this curve here, then what we would be doing, we'd be integrating this here from r1. Okay, so if this here, that point there, let's say that's the origin of our axis system, so we would be integrating that from r1, that's that point, to r2, which is that point p2 up there, of 1 upon r squared by dr. So when we integrate that there, we'll get our q naught upon 4 pi epsilon naught, and we'll have 1 upon r2 minus 1 upon r1. Now the thing to note here is that this final answer here, well, this answer here is going to be path independent, so there's no path dependence within this here, so we could have went round any path in order to get to these points r1 and r2. So the value of this integral is only going to be dependent on these points r1 and r2. So you can see that if we went any direction along here and we took any other path, we would still get the same value for this integral, because nowhere in here does it mention anything about the path. It only gives you the value dependent on the points here, the point R1 and the point R2. So let's continue on. Almost finished. So that type of force there we looked at, it's called a central force. Okay, so a central force is one, it's only dependent on the distance between the points, and the force acts along the lines joining the points. So we know that that there is what happens in terms of the Gauss's law. Okay, so Gauss's law satisfies both of these. So that's a central force, and central force are going to be path independent. So we could rewrite our equation there, and we'll replace our general field F with the electrostatic field E. So we can say that the integral around a closed path of the normal component of the electric field around that path is going to be path independent. So it means that we could draw out, say, 2 points P1, P2. We can draw two paths, that's path C1 and that's path C2. And we can say that, well, the value of the line integral is the same in that path as that path. So we can write the integral of C1 of f dot t is going to be the integral of C2 of f dot t. So it means, using just basic calculus, if we were to change the direction of C1, so the path now pointed from P2 to P1, then we could say the integral of, well, minus C1 just means the path, rather than going from P1 to P2, we're going from P2 to P1. So that's going to equal, we can take that minus sign out and just leave it with C1. It's the same as minus the integral C1 of f dot t ds. So it means that we can then write the integral of the path C2 is equal to minus the integral of the path C1. So it means then that we can say, when we add both of these together, we'll have minus C1 plus C2 is going to equal 0. But it means that this minus C1 plus C2, well, all minus C1 is the path in this direction. So what we're doing is we're going along this direction here, and we're going back down that direction there to end up where we started off. So it means that what we do is, in that case there, we put this little circular sign, so that really tells us we're going round and begin at one point and ending at the same point, round in a circle. Okay, so we're going to round, we start off at one point and then we end up back at the same point. So it means that that value there, around that closed loop of the line integral, is going to be equal to 0. Okay, so we can replace this f by our electrostatic field. So we can say that the electrostatic field, the E dot TDS around this closed loop is going to be equal to 0, and we call that thing here, we call it circulation. So in words, we can say the electrostatic field that's in the tangential direction around some closed curve is going to be equal to 0. Okay, now we're going to use that fact in order to help us find the electrostatic field given a random charge distribution. So first of all, what we're going to do is, rather than look at the circulation here around this closed loop C, we're going to look at the idea of circulation at a point, and we'll be introducing that in the next video when we look at the idea of curls. Goodbye. In this video we're going to start looking at the idea of curl. Now, in the previous video we introduced the idea of circulation. The circulation was the line integral around a closed loop of a vector function, and we took the dot product of the vector function and the tangential component only of that function. So we noted that there are certain situations where the value of this integral is path independent, meaning that it doesn't matter what path you take between 2 points, all that matters is the actual end points themselves, and those are the things that determine the value of this integral. So in that instance there, we can write that this line integral around a closed loop is equal to 0. Now what we want to do is we want to look and find this value of circulation, but we want to look at the circulation rather around this than around this closed loop. We want to try and think about the circulation at a point. So the idea of curl really is the idea of looking at the circulation at a point. So let's draw out our coordinate axes. So we've got x, y and z axes, and we've got our components I, j and k in those directions. I've picked some small volume element, and the top surface I've showed you in yellow. So the top and bottom surface make a pair, okay, and we've said see the right hand surface is in blue, so the right and the left hand surfaces make a pair, and we've also got a little pink one at the front there, so the front and the back surface make a pair. So if we start off, imagine looking from the top down. So we're looking down onto this yellow surface. So the yellow surface is going to be sitting in the xy plane. So I've just drawn that down here. So we've got our xy plane and we've got our little closed loop. Now I've called these CR for the right hand curve, although it's not a curve, it's just a straight line. So it's CR for the right hand and then the left hand, and then you've got a top and a bottom, and we're going round in this direction here. Okay, now the central point here is just our point xyz, and we know that the length of this line here is going to be delta x, and the length of the line there is going to be delta y. So if we multiply delta x delta y, we get the small area inside, which we call delta s. Now we can approximate this line integral by taking the value of the function at the central point of the line and then multiplying it by the length of the line. So let's just do that here. Now I've written out this out in full. Okay, so this line integral here, it's a vector function. So the vector function is a component in the I direction of the fx value of the function xyz, and a component in the j direction of the fy component of xyz, and a component in the k direction of the vector function, the z component of the function xyz. And we're doing a dot product of that with the tangential component. Now the tangential component we've seen derived before was going to be I dx by ds plus j dy by ds plus k dz by s all times ds. So now we're interested in the line integral along this bottom face here. Okay, so the bottom line here, that's CB. But the only component tangential to this line CB is going to be in the I direction. Okay, so we can see then that there is no j tangential component, there is no k tangential component, there's only the I tangential component. So whenever we take the dot product with the I, well, I dot I will leave us with our fx value of the function, I dot j will disappear, and I dot k will disappear. So it means that this line integral along this line CB will give us only the x component of this vector field, and then we do the approximation. We take the x component of the vector field halfway along the line and then multiply it by the length of the line. So halfway along the line, it's just going to be, we've got to come along x and we've got to come up y to get to the centre, but then we've got to take minus delta y up and 2 off to get to that point, and the point z is the same, and then we've got to multiply that by delta x. Now we can do the same for the top line. The only difference with the top line is that we're not longer going in the I direction, we're going in the minus I direction, and also the point up there is going to be given by y plus delta y up and 2. So I've just written that out there. It's going to be minus f of x at the point x, y plus delta y up and 2, comma z, all times our delta x. I've stuck in 2 delta x's there. Okay, so let's move on, and we'll also look at the right and the left hand side. Now the right and the left hand side, the only component in the y direction, in the j direction, is going to be the y component of our vector function. So if we were then to take the approximation, which is the centre point of the right hand side, well, to get to the centre point of the right hand side here, we're going to have to come along x plus delta x upon 2 and then come up y and z in order to get to that point there. So we've got this value here for the vector function and the y component of it, and then we multiply it by the length of the line, which is delta y, and then we do the same thing for the left component, but you notice in the left component that the direction is no longer in the plus j, it's now in the minus j direction. So we've only got the y component of that vector, and it's minus f of y, and it's at the point, well, it's going to be at x minus delta x upon 2 in order, comma y comma z, and the length of the line is going to be delta y. So what we do is we're going to add up 1 and 2, and we will add up, so we'll add up the left and the right, and also the bottom and the top. So we start off with the top and the bottom. When we add those two equations together, we take out the value negative, so we'll have our fx at that point there and minus fx at that point there times our delta x. Now we do the same trick here as we've been done in the previous videos when we were deriving the divergence theorems. We can multiply this by a delta y upon delta y, so that will give us the small area element delta s on the top. So then what we can do is we can take the delta x delta y down, and we'll be dividing by 1 upon delta s, and if we take the limit as that delta s, which is just a small area, tends towards 0, then we look at that in terms of the line integral. Now I've been a bit fast and loose here with the nomenclature. I just drew two little lines because we're doing here the top and the bottom, so we're looking at the line integral along the top and the bottom lines of the vector function, and we take the dot product with the tangential component of that vector function. So all we have above here then is our delta y will get subsumed within this here, okay, and we'll just have our delta y delta x is just the 1 upon s here. So whenever we do this limit, we're just going to be left with our minus, they're going to be partial fx by partial y. Okay, so that's the first part of it. Now we do the same thing with the second part. We add in the add up the right and the left components. So we add the right and the left components, you end up with the fy component of our vector at x plus delta x y z minus fy of our component at x minus delta x upon 2 comma y comma z, and if all times the length delta y. So then we can multiply by delta x upon delta x, okay, and then that means in the top line again we're going to have our little area element delta s. So we divide throughout 1 upon delta s, and we take the limit as delta s tends to 0, 1 upon delta s, and now again we're going round this closed loop, but we're only doing the left and the right components, and we're doing our multiplying our function and taking the dot product of our vector function with the tangential component. So all of that there, then the delta x is going to get subsumed within this here whenever we take the limit, and we're going to have our partial fy by partial x. So finally what we can do is we can add both of these partial derivatives together, then we're going to have the limit around the entire closed loop, and I've drawn that there as a square. So that's the limit around the entire closed loop. So that's going to be partial fy by partial x minus partial fx by partial y. And we can see that this part of it here is actually in the k direction, okay? So we've got the top and the bottom face. The top and the bottom face there is in the z component. Z is the z part of it, so it's in the k direction there, okay? So that would be the normal there and the normal there, okay, which is in the k direction, and that's the normal to the top and the bottom surfaces. Now we can do the same for the right and the left surfaces, and we can do the same with the front and the back surfaces. Now I'm not going to work through all the details, but you can go through yourself, and it's pretty straightforward. I've done it before. I just don't want to clutter the whole entire thing up here. So, but you end up with another set, two other sets of components, the J component and the K component. So this final thing here is going to be another field. Okay, so whenever we find the curl of vector field, we get another vector field, and that value, the curl, is going to be given by partial fz by partial y minus partial fy by partial z in I, plus j partial fx by partial z minus partial fz by partial x, and in the k direction partial fy by partial x minus partial fx by partial y. Now this thing here is called the curl of that vector field. So in words we can really say the curl is the limit of the ratio of the circulation to enclosed area as the area tends towards 0. Okay, so it's very similar type of derivation that we did whenever we did the divergence. Now we'll finish this off, and because there's easier ways to remember this and just a bit of nomenclature. First of all, when we looked at the normal component, we defined the normal to the surface, because we could define the normal in either that direction or that direction. So what we do is we use the right hand rule, and if in this instance here, if the direction around the closed loop is in this direction, then the normal is said to be in that direction. So this is a right hand rule. If you take your right hand, your thumb will point in the direction of the normal, and your fingers will make a loop in the direction round the loop. Okay. Now also we can see that if the line integral here, which was defined as the circulation around a path with that normal n, then if the line integral if the line integral, which is the circulation around a path with a normal n, then we can say that this limit is delta s tends to 0 of 1 upon delta s around that same loop of the vector function and the dot product with the tangential component. Well, we can say that whole thing there then is equal to the normal component dotted with the curl. Okay, just another way of writing that out. So what we can do is, in order to try and remember the curl and the different differentials for that curl, we can write it out in determinant form. So we can write out this 3 by 3 determinant. So we're going to have our I, j and our k, and we're going to have our partial by partial x, partial y, partial z. We're going to have f of x, fy and f of z, and we can take the determinant of this. So to take the determinant, it's going to be I times, and it'll be the determinant of these 4 components, and it's j times the determinant of these 4 components, and then the k times the determinant of these 4 components, and you notice actually a minus j there as well. And then we work out the determinants here, so it's going to be, you cross multiply, it's going to be the partial fz by partial y minus partial fy by partial z. Okay, so that's what we've written here. The only thing to note here as well is there's a minus sign here, so it just swaps these 2 round about. But whenever you work through that, again, we get our value for the curl. Now a neat way of writing that there is, we remember that we had the del operator, and we've seen the del operator, there's a video on it a couple of videos ago, and it's going to be our I partial by partial x plus j partial by partial y plus k partial by partial z. So we can see then that we can write the curl as the del operator cross product with our vector function f. So that's really the point we wanted to get to there. Okay, so that gives us the idea of our curl of our vector field. Now here's a simple example just out of the book that was using there. We had some function x, y and z given by I xz plus j yz minus k y squared. Then to find the curl of that vector field, we write down our determinant here, and then we just work through this determinant. So we're going to have our, in the I direction, we're going to be our partial, it's going to be partial minus y squared by partial y, which gives us minus 2y, and it's going to be our minus our partial yz by z, which is going to give us our minus y, and then we do the same for the j direction, the j one, and we get the partial by partial x of our minus y squared and our partial by partial z of xz. These two things, xz is going to give us a value of minus x, and the other one's going to have a value of 0. And then finally the k component is going to be the partial of these cross multiplied, okay, which again is going to give us 0 and 0. So whenever we add these two up, we just get minus I times our 3y plus j times our x. So the actual working out the curl is relatively straightforward, and it's a nice process whenever you're remembering it via the idea of the determinant. So that's all there is for this video. In the next video, this has been kind of a bit kind of mathsy. It's maybe not going to be a great intuition as to what curl is. So the next video will be a video about an intuitive understanding of the idea of curl. Okay, so thank you for listening and goodbye. In this video we're going to look at 3 examples in order to give us an intuitive understanding of what we mean by the term curl. Now I've drawn out these vector fields in Matlab, and I'll leave the M files there available to you so you can go and have a look at these yourself and create your own vector fields. It's quite straightforward. So in this here, you can imagine this as, say, water going down a plug hole. So say the plug hole's at the centre and the water just rotates round about and down the plug hole. Now it's a bit of an approximation here, because in reality what happens is that the water will travel slower on the outer face here, and will actually speed up as you get closer and closer to the centre. Okay, so the angular velocity will increase, but we'll just make the assumption that it's actually travelling around at the continuous angular velocity all the way into the centre. So if we were to draw out this little section here, so just draw a little section. It's actually meant to be a circle, but it looks elongated because it's been done on a 16 by 9 screen. Okay, but it is actually meant to be a circle. So we take a point there in the circle xy, and we say that the radius is r. Then we can see that the angular velocity there is going to be given by our omega. Now if you're unsure about angular velocity, then there's a little video up here. If you click up here, it'll take you through the snippet section that describes everything you need to know about angular displacement, velocity and acceleration. So in this example, we can see that the x point here is going to be given by x equals r cos omega t, and you can see that there. If you drop that perpendicular here, then we can say that this distance here, call it x, so x upon r would be the cosine of that angle, so x would equal r cos omega t, and the same up here, you're going to have your y is going to equal r sin omega t. So this has got these two equations here. Now if we were wanting to find out the velocity, then we could split the velocity into the I direction and the j direction, and we can differentiate the displacement with respect to time and the x direction displacement with respect to time in the y direction. And when we differentiate these, we'll take out the common factor of r omega, and we'll see that the first term here is going to give us our minus I sin omega t, and the second term here is going to give us our j cos omega t. So what we can do is we can keep that common factor of omega out, and then we can notice that the r sin omega t, well, r sin omega t is just our value for y, so that's just going to be our iy, and our r cos omega t, well, r cos omega t is just our value for x, so we can just put in our plus jx. So we're left with this equation here, which will give us a velocity field. So it will tell us the velocity of a particle placed at point xy within this field. So the velocity is going to be omega times minus I times y plus j times x. Now if we were wanting to, we could look at that and try and find the curl of this field. Okay, so we have the intuitive understanding that the curl is in some way is related to the circulation. So we can see here that if we were to place a component or something within this field, we know it's going to rotate. Okay, the fact that it's going to rotate
tells us that it has a curl associated with it. So let's go and we'll work out the curl. So we've seen from the previous video that we can write out the curl here in terms of the determinant. So we can write it as omega, so we'll keep the omega there, and we'll get the determinant I giant k of partial by partial x, partial by partial y, partial by partial z of their function. In this here case here, our function is just going to be, well, in the I direction, just going to have minus y. Okay, so we have our minus y here, and in the j direction, we're just going to have the value of x, and in the k direction, well, we're just going to have the value of 0. So then we take the value in the I direction, so in the I direction here, and we cross multiply these, so it's going to be 0 for this, partial 0 by partial y is 0, and this partial x by partial z is going to be 0, okay, because we're differentiating with z and x is not a function of z, okay, so that gives us a value of 0. So we've got the 0 for the I component, and the j component, we cross multiply the two outer ones, okay, so we're going to be partial 0 by partial x is 0, and it's going to be minus the partial z by minus y. Again, y is not a function of z, so that's just going to give us a value of 0. The third term here is the k component. The k component is going to give us we're using the I and the j, so it's going to be partial x by partial x, which is going to give us a value of 1, and we're going to be minus partial of minus y by partial y is going to be minus 1, so it's going to be 1 minus minus 1, which is equal to the value of 2. So you get a value factor of 2, and it's in the direction of k, and it's times the value of omega. So the curl of that field is 2k omega. Now we can see then that in this instance here, the curl is 2k omega, so the curl is really directly proportional to that angular velocity, okay, so as the angular velocity increases, the value for the curl increases. Now we're interested as well about the direction of this, so we're saying this is equivalent to having a vector in a direction k, okay, so if we were to draw out this circle in the xy plane, and we can see it's rotating round in this anti-clockwise direction, then we say that the value of the vector k points up the way, okay, so we're going to have the value of k is going to be 2kw, so that represents, that vector there in blue represents the curl of that vector field. So we're going to use, as mentioned in the previous video, the right hand rule. So if you were to take your right hand and you put your thumb up, and the fingers would curl round in a direction, so we're going round in that direction, and the direction of the thumb would give you the direction of the normal. Okay, so that's the first example, and it gives you a good indication of the idea of the curl of a vector field. So we're going to example number 2. So example number 2, and these are just really taken from the book that I've been using, and I've again drawn out the example in Matlab, and these are the vectors here, and we can see that the variation is in the y direction, so you can see that the further down in the y direction here you go, the smaller the velocity, and it accelerates as it gets towards the x direction. It's at maximum acceleration at the velocity, sorry, at the origin, and then it starts to slow down again as we go further away from the x-axis. So this is the equation here that we're looking for. Okay, so this is the equation of that vector field. J v naught e to the minus y squared upon lambda squared. The lambda is just some constant, and v naught will be some constant as well. So whenever we work out the divergence of this field, we've got I giant k, the same as usual, and now here we've not got any factor of x. Okay, there's no velocity part of that vector field for velocity in the I direction, so there's nothing there, and there's no velocity in the k direction either, but there is a velocity in the j direction, which is vo e to the minus y squared upon lambda squared. And again, we'll just go through the differentiation here. So we take I, and then we cross multiply and differentiate these, and we've got 0 for that and 0 for this as well. And we do the same for the j, and if we do the j, we're going to have these cross multiplied, the two end ones, and these cross multiplied, which is going to give us 0. And we're going to have the k as well, so the k is going to give us these two here and these two, and again there's no factor of we differentiate with respect to x, and there's no x within this here, so that's just going to give us a value of 0. So it's going to give us 0 for curl for this entire field. And you can kind of see this here, because if you were to have a little paddle sitting in here, then all the velocity vectors are the same magnitude that hit this paddle, so it means that the paddle won't actually spin. Okay. Now we'll move on and we'll see a similar example to this. Okay, so let's bring that up. So the final example here is very similar, but we now have the velocity vector being given by gi vo e to the minus x squared upon lambda squared. So there's going to be a variation in the velocity in the x direction. So as we go towards the centre here to the y-axis, the velocity is at a maximum, and then as we head up along the x-axis, the velocity vector becomes smaller and smaller, and the same in the opposite direction. Okay, so we're going through the same process here. We'll work out the curl for this vector field here, and again there's nothing in the I direction, nothing in the j direction, but in the k direction we're going to have the partial by partial x of v naught e to the minus x squared upon lambda squared minus the 0. So this is the only factor here that I'll actually add into the curl. So when we differentiate that there, we're going to get this minus k v naught 2x upon lambda squared e to the minus x squared upon lambda squared. Okay, so this here actually has a curl, and you can see that there because if we were to look from above and we had a little paddle sitting in this vector field, then you can see that as the velocity varies in this x direction, we could have a large velocity here hitting this paddle and a much smaller velocity hitting this paddle. So it means that the paddle would tend to turn in a clockwise direction. So if we were to actually split this into the 4 components as we've done previously when we derived the idea of curl, then we could look at the direction round about. If we take a point x, y, we could really look at the direction from the bottom paddle, the top, and the right and the left paddle, and we can see that the right paddle here is going to equal, well, it's going to be equal to the velocity in the y direction times the delta y at a point x plus delta x. That's x plus delta x, which is this point here. Okay, we're going to have our velocity in the left hand paddle, which is this paddle here. So velocity in the left hand paddle, well, again it's in the opposite direction. That's the plus direction for the j. This is going to be a negative direction. Okay, so it's going to be our minus v of y at a point x there, so that's the point x, times the value delta y, which is this length here. So these two terms are going to be different. Okay, so because the two terms are different, if you're adding them up and working out the curl, we will actually get a value for the curl. But the two terms up in the bottom and the top, those would be exactly the same, and there wouldn't be any curl associated with those. Okay, so that gives you a little indication of some examples of curl and how to work out the value of the curl. Now I'll put a wee snippet at the end of this as well, because you can get into Matlab and you can stick in these vector fields in Matlab, and then you could have Matlab work out the curl of the vector fields for you. Okay, so I hope this was good, and I hope it was worthwhile, and I'll get you in the next video. Goodbye. In this video we're going to look at curl in cylindrical coordinates. So I've drawn a little volume element out here, and it's got faces 1, 2 and 3, and we're going to look at the line integral around each of these faces. So initially we'll look at from the top down onto face 1, and I've redrawn that out here. So we're looking down onto this xy plane, and we can see that we'll have a angle delta theta, which is this little angle in here. We'll have a delta r, which is this little distance here, and we're going to work around the face in an anti-clockwise direction. So we'll go along path 1, 4, 2, then 3 in that anti-clockwise direction. And you can see that this little area in here is going to be given by our r delta theta, which is going to be our distance here, and our times our delta r, which is our little distance there. So that'll give us that area. So what we're interested in is looking at, first of all, the path 1 and 2. So what we do is we approximate this integral here by looking at the value of the vector function at a point in the middle of the path, and then multiply it by the length of the path. Now, the first part here, 1 plus 2, we're looking at the vector function, and it's the dot product with the tangential component. So the only component here that's going to be left after that is going to be the component that's going to be in the r direction. So we'll have f of r, and it's going to be at this point here. So that point there is going to be given by our, well, that point here is our r theta z. So it's going to be our r, but it's going to be our theta minus delta theta upon 2, and also to get up here is going to be our theta plus our delta theta upon 2 to get to this point here. And of course it's all going to be multiplied by the length, and the length here is simply our delta r. So I've got that down here. So we've got f of r at point r, theta minus delta theta upon 2 comma z, and it's going to be the minus f of r because this direction here is a positive r, this arrow here is in that direction, so it's going to be a direction of minus r, so it's minus f of r theta plus delta theta upon 2 comma z, all times our delta r, just taking out the common factor delta r for both of these. Now, if I was to multiply that top and bottom by r delta theta, then we'd be left with the little area element there. So this top line here gives us the area element. So now if we were to take the limit as delta s tends to 0 of 1 upon delta s, which is just the surface area of the f dot t, we're going to be left with, well, we'll have an extra factor here of r left over. Okay, so they'll have a 1 upon r, and it's also going to be a negative because this is the first term here, the theta plus delta theta upon 2, okay, and that's the second term here, so we'd have to multiply both of them by a negative to get them round the right way. Okay, so we're going to be left with minus 1 upon r, and it's partial fr by, and it's the limit is delta theta tends to 0, so it's going to be delta theta. So that's one of the 6 terms that we're looking for. So the second term is very similar. We're looking for the face. In this case we're looking at lengths 3 and 4. So in this instance, in order to get to 3 and 4, well, we've got to go to r theta z. Okay, in order to get to 4, we're going to have to head up along our r plus delta r upon 2 to get to face 4, and it's going to be r minus delta r upon 2 to get to face 3. And also there's an added complication because the actual size of that arc is going to be equal to our r minus delta r upon 2, which is this distance, times our delta theta, and our r plus delta r upon 2, which is the big distance, times our delta theta. So I've added that in here to this equation here, and we've got our, also note, we've also got the face 3, it's in this direction here. So if the positive theta direction is anti-clockwise, this is going clockwise, so that's going to be a negative value for that. So we're going to have our minus f of theta at point r minus delta r upon 2 comma theta z, and the distance is going to be equal to our r minus delta r upon 2 times our delta theta, that's the size of the arc, plus f of theta r plus delta r upon 2 theta z times the length of the arc for length 4 is going to be r plus delta r upon 2 times our delta theta. Now, if I was to multiply these again by our r times our delta r upon r upon delta r times delta r, then the top line here, the delta theta r delta theta, will give us again the small area element 1 upon the delta s. So I can take the limit as delta s tends to 0 of 1 upon delta s of the lengths 3 and 4, and f dot t ds is going to give us, well, again, we're going to be left with this extra term 1 upon r out here, but we're also going to be differentiating it, so with respect to r, so we'll have a delta partial r, but what we're going to differentiate is we're going to have our f of theta times, and this extra term here is going to add in an extra r, okay, so the delta r will tend towards 0, and this is going to tend towards our value of r. So this is our second term here, which we're looking for. So the other four terms are along a very similar vein, we're just looking at different faces. So this case here, we're looking at face number 2. Now face number 2, you notice that the area of that face number 2 is going to be given by this length here, which is going to be our r delta theta, and this length here, which is going to be our delta z. Now, if we were to go along round the anti-clockwise, 1 to 3 to 2 to 4, and we notice that the integral of from along the lengths 1 and 2 over f dot t will the only and within respect to 1 and 2, the only part of the vector function which is going to exist is going to be along the theta direction, okay, the angle theta. So that's this angle here. So we're going to be f of theta. Now in order to get to points 1 and 2, we're simply going to add on our z plus delta z upon 2 will take us to this point, and z minus delta z upon 2 will take us to that point there. And the lengths here are going to be given by our r times delta theta, which is just the length of that curve, assuming all the angles are in radians. Now what we can do, the same trick again, we can multiply this thing here now by delta z by delta z. The top line will give us our area element s, and then we take the limit as delta s tends towards 0 of 1 upon delta s over our 1 and 2 f dot t ds. So that's going to be given us, well, notice here again that we're going to have our z plus delta z upon 2 on this side here, which is negative, and z minus delta z upon 2. In order to get them round the proper way for the differential, we multiply everything by a negative. Okay, so we end up with a negative partial f of theta by partial z, and there's no extra term there. Okay, so that's that's part number 3. Now the next part is going to be for lengths 3 and 4. Okay, and you can see in order to get to 3 and 4, you're going to have to add on our delta theta upon 2 and take away delta theta upon 2 in order to get to those points there. Okay, so we've done that here in this one. So we've got the only component of 3 and 4 is going to be in the z direction, and the point is going to be f of z at point r theta plus delta theta upon 2, which is going to give us our value for our 3, and our theta minus delta theta upon 2 is going to give us our value for our point 4, and the length is delta z. If we were to multiply then by r delta theta, this will give us the area element, and then we take the limit as delta s tends to 0 of 1 upon delta s over 3 and 4 of this f dot t. It's going to give us our, well, we're going to be left with an extra term here, which is our 1 upon r, and it's going to be partial by partial theta of f of z. Okay, so that's the fourth one, so almost there, so another 2 to go. So the next thing is the last face here, and we can see it's going to be given by our distance. We'll say we're going round this here in a clockwise direction through 1 to 3 to 2 to 4, this distance delta z, that's delta r. The area is just going to be delta z times delta r this time. So we can see then that for lengths 1 and 2, in order to get to 1 and 2, what you've got to do is you've got to take, go to point r and take away delta r upon 2. In order to get to this point here, you've got to add on delta r upon 2, and again the lengths here are just going to be equal to our delta z and delta z. So this is just going to give us f of z at r minus delta r upon 2 theta z minus f of z r minus delta r upon 2 theta z all times delta z. Now we could multiply that whole thing out by delta r in order to give us the area element upon delta r, and then if we take the limit as delta s tends to 0, 1 upon delta s of that integral 1 and 2 f dot t ds is going to give us, well, again here, in order to get this in the right form, that's actually minus, that should say plus. Okay, in order to get this in the right direction, we're going to have to multiply everything throughout by a negative, so that the r plus delta r comes first, and then you're taking away the r minus delta r. So that's going to give us minus partial by partial r of f of z. There's no extra term there. Now we do the same thing again, only we're going to do the same thing for lengths 3 and 4. Okay, so this is lengths 3 and 4. In order to get to 3 and 4, we've got to add on our delta z upon 2 and take away our delta z upon 2, and the distance here is just going to be our delta r. So this equation here is going to give us that, and again we can multiply it by delta z upon delta z. So having done that, we take the limit as delta s tends to 0 of 1 upon delta s of the line integral. It will give us our partial f of r by our partial z. So that's going to leave us with the 3 equations here for our curl. So I'll just read them out. The curl of the vector function f with respect to r will be 1 upon r f of z partial f of partial, that should be partial, f of z by partial theta minus partial f theta by partial z, and it'll be the curl of f with respect to theta will be partial f of r by partial z minus partial f of z by partial r, and the curl of f with respect to our z will be 1 upon r partial by partial r f of theta minus 1 upon r partial fr by partial theta. Now, not the most exciting or interesting video, I'll give you that, but it's a bit of bookwork, and it's the sort of thing that if you've seen it once and you read through it once and you can understand it, it's worth doing it just for that one time. Then you know how it's worked out, you know where the equation comes from, and you're happy to then go ahead and use it. Okay, so thank you for listening, and I'll get you on the next video. Goodbye. In this video we're going to derive the curl in spherical coordinates. So in spherical coordinates we have our radius r, we have an angle here in the xy plane which we're going to call phi, and we have an angle that we can drop down onto the point on the sphere, and we'll call that angle theta. So we're going to look at it in terms of 3 different faces. So there's going to be one face here, face 1, and then face 2, and then a third face here. So the first face is the one that we're going to look at here at the moment. So we've drawn out the little route which we're going to work out the tangential integral roundabout. So we're going to have face length 1 and 2, length 3 and 4. So it's the same as we've done in the previous examples. The only difficult thing about this is actually just working out what the area elements are. Now in this instance here, the area element is just going to be our r delta theta. So r delta theta is going to be this length here times the value delta r. So that's the delta r here. So we could say that the integral along length 1 and 2 of the tangential component of the force is going to be approximately equal to, well, the only component in the tangential direction here and is the component in the theta direction. So it's going to be our f of theta, and at face 1 it's going to be r plus delta r up in 2. So we come out r and then we come out the little delta r up in 2. And we've also got to work out the length. So the length of this section here, well, the length of the section there is going to be r plus delta r up in 2 times the angle of theta, which will give us this length here, the arc length at 1. And we're going to take it, and it's going to be minus f of theta, because theta is defined in this direction. So heading up here, using the right hand rule, this is going to be a negative value. So the point we're going to have is the point r minus delta r up in 2, and it's going to be theta phi, and again the length of this little arc here is going to equal the r minus delta r up in 2 times the value over theta. And it's all, we've taken out here the common factor of the theta out of both of these, so there should be a bracket around about that there. Okay, so we've taken out the common factor over theta here, and if we are going to then create this area element, we're going to have to multiply that by r delta r. So we'll multiply the top and bottom lines by r delta r, and then we can take the limits delta s tends to 0, 1 upon delta s of this f dot t. So that's going to give us, well, it's going to be partial f of theta, and we're going to have an extra term in here. The extra term here is going to be from here, the r term. So it's partial f theta r, and it's differentiated with respect to r, and we're going to be left with 1 extra r at the bottom. So we end up with this first part here. So that's the first of 6. Now the second one we're going to do phase 3 and 4. So we do phase 3 and 4, and the phase 3 and 4, well, the length of phase 3 and 4 is just the delta r. So we're going to be working along the direction fr, and the first one's going to be a minus. That's phase 3 because the r is defined out the way, and this is direction of 3 is faced in the way. Okay, so we end up with our minus fr, and that's at a point r, and it's theta plus delta theta up in 2. So that's the angle of theta there, coming down to there, and we add the delta theta up in 2 just to get to this centre point here. And of course we'll be multiplying that by a delta r, which I've just taken out. And the other phase 4 will be the similar, only difference is we're going to the point theta minus delta theta up in 2. So that means that in order to get the small area element, we've got to multiply by r delta theta upon r delta theta, and then when we take the limit here, we've got our, now we have to be careful here because we wanting this term has to be first. Okay, so that means that we've ended up with a minus 1 upon r, so that's the extra r there, partial fr by our partial theta. So the curl in the phi direction is going to be given by 1 upon r partial r f of theta upon partial r minus 1 upon r partial fr by partial theta. So you could just read over that and check it and convince yourself that what I say is true. Now for the second face, so this is this face here. Okay, now the area of that face there, well, it's got to be this distance here, so that distance here has got to be our r delta theta, so we get our r delta theta. Now this face along here, it's going to be, well, if we were down at this point here, it would be our value of r, and it would be delta phi. But as we work our way up along here, you'll notice that this distance gets smaller and smaller. Well, it gets smaller and smaller by a factor of the sine theta, which is this, theta is this angle as we drop down here, is this angle. You can see that down at the bottom there, the theta is equal to our 90 degrees, so it's equal to our 90 degrees, so which gives us a full value there of this length, and up here is equal to our 0 degrees, and it's going to give us a value of 0. Okay, so the length here is 0 because we're starting theta from this point down to that point, so that's our 0 degree point and that'll be our 90 degree point. So we ended up with this area element here, okay, r delta r times r delta phi sine theta. Now we're going through the same process again. Now I don't really want to go reading through all of this. The mathematics is really there in front of us. I'll just maybe go through this one and then I'll leave the rest of the maths to you have a look over. So we're going to have our 1 and 2. So in this instance here, that's our 1, that's our 2. So it's only got a component. The vector field's only got a component in the theta direction. So we'll have our theta, f of theta, r times theta, and for number 1, well, this is the phi direction here. Okay, so that means when we go from here bound to point 1, we've got to go along phi minus delta phi upon 2, and to get to phase 2 it's going to be phi plus delta phi upon 2, and that length there is just going to be our r delta theta. So that's our r delta theta there for both of them. I've taken them out as a common factor. In order to get the area element, we've got to multiply by r delta phi sine theta upon r delta phi sine theta. And if whenever we take the 1 upon delta s, which is just going to be the top line here, down, we're going to be left with just r delta phi sine of theta. So another thing to note here is that we want this term to be first because that's the theta plus delta phi upon 2. So we've got to multiply everything by a negative to get this term to be the first term. Okay, so that's going to be end up with a negative term there. So we've got a minus 1 upon, and what's left over there is going to be our r sine over r sine of theta. Okay, so that was going to give us minus 1 upon r sine theta partial f of theta by partial phi. Okay. Now we do the same for phase 3 and 4, but now we're going to have our theta plus delta theta upon 2 and theta minus delta theta upon 2. So that's phase 3 and 4, and we're going up from that point there. We got up theta upon plus delta theta upon 2, and then we come down. We actually, for phase 3, we go from that point theta plus delta theta upon 2, and phase 4 is theta minus delta theta upon 2 because theta has been defined in positive as in that direction. Okay, so that's going to give us our one thing to note here as well in this particular one is that the length element is going to be given by our theta, our sine theta plus delta theta upon 2. Okay, because these length elements are different. Okay, they're dependent on this sine of this angle. Okay, so we're going to have the sine theta plus delta theta upon 2. So it means that this sine theta becomes part of the differential here. So we're left with this term here. So the curl in that direction r is given by this equation here. Now the same sort of thing applies to the third one, and this time we're interested in this top face here, and this is the area of that face there. Okay, and again we work through for 1 and 2, and if you work through the maths here, we're going to end up with our one term here. And again, I don't want to read it all over because it's a similar thing that we've done in all the previous examples. And then phase 3 and 4 is going to give us this here. And when we put these two together, we're going to have the curl, and the theta direction is going to be given by this equation. So that's all three sets of equations that we use in order to generate the curl of a vector field in spherical coordinates. Now I didn't want to read through every single detail of it because you can see that it's a very, very similar approach that we've used to all of the other videos. If you watched the previous videos, you've probably seen it all, and it's all kind of getting stuck in your head now. Okay, so that's all for this video, and I'll get you on the next video. Okay, thank you and goodbye. In this video we're going to look at the differential form of circulation. Now ostensibly we've already covered most of the work in this video and the previous 3 videos, so we're really just covering a few loose ends here. So we've seen this equation here in the previous videos, and on the right hand side here we have the circulation, which is the dot product of the vector field with the tangential component, and that's the line integral of that round some closed path C. And then we take the ratio of this quantity here to the surface area enclosed by that path C as the surface area tends towards 0. Okay, bit of a mouthful that. So this thing here is equal to the left hand side here, but we have to note here that this thing here itself is just a scalar value. It's only given a direction because we have applied this in a particular direction dependent on this surface C, and we've seen that in the previous videos when we derived the curl in the 3 different coordinate systems. So we derived it in terms of a Cartesian, a spherical and a cylindrical coordinates, and we generated this equation here 3 times. In the Cartesian we chose the normal to be first of all in the I, and then in the j, and then in the k direction, and when we summed those up we got the curl of the vector field. So right now this n dot curl f is actually gives us a scalar coefficient. It's not until we sum them that it gives us the full curl. Now that's really just what we've got stated down here. The surface area here that we are working on, that can point in any direction. So as I said, we've judiciously chosen a particular coordinate system, and we've chosen it the examples that we've seen in the previous videos. Okay, so now we're going to look at the circulation and the curl in terms of the electric field. So this will just finish this off for us. So if we were to put the electric field in for our vector field here, then we've seen from a previous video that the circulation of a vector field of an electric field is going to be equal to 0, and there should be a little hat over the top of that. It's electric field. So we're really saying that the electric field it is conserved. So we can then write this here, and we can say that in that case then, if this thing here equals 0, then the thing on the left hand side here equals 0. So we can say that n dot curl E equals 0, but we know we're choosing the n in terms of our directions I, or j, and our k. Okay, so we can say then our curl of the electric field there is equal to 0, or we can write it in terms of the del operator as we've seen in the previous video, and we can say the del cross E equals 0. So this here is the differential form of the circulation law, which we have already seen in the previous videos. So the question that we had asked a few videos ago is, can a given vector function be an electrostatic field? Now we've got an answer to that. The answer is if the curl of the vector field is equal to 0, then it is yes. If the curl of the vector field doesn't equal 0, then the answer to that is no. So here's an example here. We've got our vector field f, which is some constant times iy plus jx. So when we work out the curl, we have our I, j and k, partial by partial x, partial by partial I, partial z, and we're going to have our vowels, so we're going to have our y here for our I and our x for our j, and we'll have a 0 for our k. So we can then rewrite that as the I of the cross here, so it's going to be partial 0 by partial y, and it's going to be partial minus partial x by partial z, and you can work through the other two here to get these other two. Partial x by partial x is 1, partial y by partial y is 1, so that's 1 minus 1, so the k disappears. These are 0 here, and in this case x is not a function of z, there's no functional dependence of x on z, and y is not getting any functional dependence on z, so it means that we're going to have 0 plus 0 plus 0, so the answer to that is 0, so that means that this then could be an electrostatic field. So that's all there is for this. We're going to move on, we'll look at Stoke's theorem on the next video. Okay, goodbye. In this video we're going to take a look at Stoke's theorem. So Stoke's theorem relates the integral around a closed path to the surface integral of a surface capping that path. Now, a bit of a mouthful again, but it's really quite simple. So if we think about a capping surface, if we have some closed loop, say C1, I've also drawn a second one there, C2, then if we imagine we had a membrane over the top here, so that's in blue, then this membrane here would represent a capping surface. So we could think about that there, if you like, as a swimming cap. So the circle around here is the circle of your forehead, and the cap is the rest of your head with a cap on it. So what we're going to do now is we're going to take this surface, and I've drawn one out again down here, and we're going to split the surface into little polyhedra, and these polyhedra we're going to sit normal to the surface. So they're just going to, they're going to sit tangential to the surface, so they're just going to cut the surface at one point. And you could imagine taking these little polyhedra, and we could take a limiting process where we increase the number of polyhedra to infinity and we decrease their areas to 0. So eventually when we do that, then all these little polyhedra will eventually become a continuous surface, as opposed to being a linear jagged surface. So then what we're going to do is, after we've split that into the little polyhedra, we're going to look at the circulation around each of these polyhedra, and we're going to use the right hand rule as well. So the normal will be coming out towards us here in this little area C1, and we'll be going round in an anti-clockwise direction, and we'll be looking at the circulation around that. But what we're going to do is we're going to just not look at the circulation just around one, we're going to look at the circulation around the next adjacent one and the one after that, and we're going to add up the circulation around all of these, and we're going to make sure we use the right hand rule for all of them. So the circulation is going to be given by the tangential component of the vector field around your path. I've called that path C1. So if we sum up all of these paths from, let's say, L equals 1 to n, so L is the nth path and n is the total number of the little area elements, so that would be down here would be a CL. So we're summing all of these circulations up for all of these little area elements. So the assertion we're going to have is that once we've summed up all of those little circulations, then what we're going to be left is just the circulation over the capping path So if we go back there, you'll see that. So if we were to look at this little path here, and then we were to add on the circulation around this little path here, well, the adjoining path is going to have equal but opposite circulation. So the adjoining path won't add any value to the overall circulation, and you can see that whenever we go into a little drawing here. So I've drawn two of the paths together. So there's one of the paths here, and there's the adjacent path here in pink, and you can see that the circulation here around this path 1, you could just call that path 1 and that path 2. And then the circulation around that path is in pink, the circulation around that path is in yellow, and we can see that the yellow and the pink here are equal but they're opposite for the adjacent path. So it means that these cancel out, so you're only going to be left with, in the end, the circulation around the outer perimeter. So that's going to disappear, and you're going to be left with just the circulation around the outer perimeter. Okay, so that's what this little equation here is telling us. So I've rewritten that again. So we're really saying that this factor of the circulation from A to B is equal to the negative of the circulation from B to A. So we can take this over to the other side. So when I add both together, we're going to get 0. So now what we're going to do, we're going to take this bit of information, we're going to continue as we did when we did the divergence theorem a few videos ago. So let's finish this off here. So we've seen this here from just the previous page there, from summing up the circulations over all of the paths is equal to the circulation round about the perimeter. Now what we're going to do is we can multiply by the small area element delta SL and divide by that delta SL as you've seen that done previously as well whenever we did the divergence. And what we're going to do is we'll do that and we'll take the limit as the number of the faces tends towards infinity and the area of the face tends towards 0. And we'll bracket off this little section here because we've seen this before. This is nothing other than, from the previous video, the normal component of the curl. So it means that when we take this limit here, we're forming a surface integral. So we're forming the surface integral of the normal component of the curl of the vector field. Now, one other thing to note here that's maybe not obvious from the size of the drawing is that the perimeter here in yellow is actually the jagged perimeter that follows these linear polyhedra shapes. So as the number of these polyhedra tends towards infinity and the area of them tends towards 0, it just tends towards a continuous path represented by C. Okay, so down here we can then write that this value here, the integral round about the perimeter, will tend towards the integral around about a continuous path C. So it means that we can write this thing up here, okay, which just equals the perimeter round about the C, is now equal to, from what we worked out here, the normal component of the curl over the surface, the capping surface. So finally we can write out Stoke's theorem here, which tells us that the normal component of the curl of a vector field over a surface is equal to the line integral around about a path of the tangential component of that same vector field, where the C is the root over which the surface here has been capped. Okay, so you can kind of get an intuition for this if you were to say draw out some general surface here, and when we think about the curl, we're thinking about, we're thinking about the curl of the field. We're thinking about what happens whenever a small microscopic area here, and what happens, let's say for example it was the eddy currents in some surface of a water, so if we drop the leaf in, it would start twisting round. So we're looking at these microscopic twists, but we've seen that these microscopic twists, if we were to take one adjacent to another and we were to form the right hand rule for these, we could see that this would twist in this direction, and this would twist here, and that would twist here. But if we were to form the same right hand rule, then we would be saying that the second one here would twist in this same direction, but if this point here was touching that point there, then this twist and the pink twist and the blue twist would cancel. So all we would be left with would be the twist from the actual perimeter. And then if we were to take that up to all of the rest of the values here, all of the rest of these microscopic areas up to a macroscopic level, then all we would be left with would be the circulation round about the line which is encloses all of this area which we've actually been looking at. Okay, so that's a kind of wordy or a kind of a heuristic or intuition behind the Stoke's theorem. So what we're going to do now is we're going to look in the next video and see where we can use Stoke's theorem. Okay, so thank you for listening, and I'll get you in the next video. In this video we're going to look at an application of Stoke's theorem. So what we're going to do is look at Ampere's circulation law, and we're going to use Stoke's theorem in order to change it into a differential form. Now, we're not going to be proving any of this, it's just really just a statement, and we're going to show you that that Stoke's theorem is actually of use within electromagnetics. So the Ampere circulation law tells us that the current through a wire is going to be equal to the circulation of the magnetic field around that point in the wire, where this term here, mu naught, is the permeability of free space. If you like, it's a measure of a kind of springiness of free space. We can get into that at some other point in a different video. So what we'll do is we introduce the idea of a current density. So the current density is a value J. So then we can say that the total current is going to be the current density times the actual area that the current passes through. And we're only interested in the normal component of that current as well. So we can see then that the total current is going to be the surface integral of the normal component of that current density, and that's the little surface there that is passing through. So it means then that we can rewrite this equation here. We'll keep the left hand side as it is, and the right hand side will now be written in terms of the current density. So we're going to be left with this equation here. So the circulation of the magnetic field is going to equal the current density, which is the normal component of the current density over a surface times the mu naught. So now we're going to use Stoke's theorem in order to change this into a differential form. So we can see that the left hand side here remains the same, but we can see then also that from Stoke's theorem that the surface integral here can also be related to the surface integral of a related quantity, which is the normal of the curl of the magnetic field. So it means then that we can take out these factors here, the curl B and the mu J, and we can write the curl as the cross product. So we're going to be left with our del cross B equals mu naught times J. So this here is the differential form of Ampere's law. It's just a quick video just to show you that we do actually use this, and it is useful within electromagnetics. Okay, thank you for listening, and I'll get you on the next video. In this video we're going to look at simply connected regions and path independence. So this is just an extra add-on, and it will be useful for us in the next couple of videos. So what we want is Stoke's theorem to hold true for some region in 3D space. So we can call that region D. So for example, two examples here. The region D here is a sphere, and the region D here is a torus. Now we want it to hold for any closed curve C which actually lies in that region. So there's a closed curve C there in pink, which lies within the sphere, and here's a closed curve C in pink which lies within the torus. But we also want it to be true for any capping surface round that closed loop. So in this instance here you can see that we've drawn a capping surface in blue, and it holds true for any capping surface of this C within the region D. So the capping surface here you can see is held complete within this region D. But the same isn't true for the torus, because if we were to draw the capping surface, then the capping surface would always come outside of the region D of the torus. So it means that what we require is true for the sphere but not true for the torus. The difference between the sphere and the torus is we say that the sphere is simply connected and the torus is not simply connected. So let's see how that relates to path independence. We've seen before that the circulation of a vector field F, if the circulation equals 0, it implies that the curl of the vector field equals 0. So we're going to ask the question, does the opposite apply? Does it, if a curl of a vector field F equals 0, does that imply that the circulation of that vector field also equals 0? So when I say that, I should use the word converse. Does the converse apply? So let's have a little look. Now it's just really a statement. The statement is that the answer is yes, that the converse does apply as long as the region is simply connected. Okay, so it means that the curl F will equaling 0 will imply that the circulation equals 0 only if the region in which it acts is simply connected. So putting it in words in terms of path independence, it really says that if the circulation is path independent, then the curl of the field equals 0, and if the curl of the field equals 0 in a simply connected region, then the circulation is independent of path. So we'll be using these couple of facts whenever we go to look at the next couple of videos. Okay, thank you for listening, and goodbye. We're going to take a look at curl in Matlab. Now we're going to be referring back to a video which we did previously called Curl Intuition. There were 3 examples in that video, and we're going to work through those 3 examples in Matlab. So if you'd like to, you can go back to that video and remind yourself of those examples. So in the first example, we're looking at a vector field given by minus y in the I direction, x in the j direction, and 0 in the k direction. So we're really saying in the z direction there's no variation, and we're doing that just to try and simplify things a little bit. Okay, so this field is drawn out here in Matlab. Now you have access to an M file that will allow you to go and generate these for yourself, okay? But we'll talk through it first and then we'll go on and we'll have a look at the examples in Matlab. So let's imagine that we stuck a paddle in this field, and you can see this field is rotating in the anti-clockwise direction. So you can see then that there's going to be some force striking this paddle in this direction and some force striking the paddle in that direction, which is going to make the paddle turn in an anti-clockwise direction. So it means from the right hand rule that the vector given by the curl is going to be in the k direction, and we've seen from the derivation done in the previous video called Curl Intuition that the curl is going to be given by the value 2kw, okay, where w is the angular velocity, and you can see here that that's just what's been generated in Matlab. We're going to have a value of 2. Now again, I've just drawn this out in a kind of simplified format. At this point here we'll have the curl will be in the k direction, so this is up here, the k direction, and it will have a magnitude of 2. If you like this blue, this yellow square here represents the magnitude of the curl, but each point here would just have a line heading up and it would be height 2. Okay, so that shows the curl and it shows it in Matlab, and we get the same results as the derivation that we did in that previous video. Now we'll show you that in Matlab just now, so if I bring up Matlab we can get that to. Okay, so in Matlab there's a file that generated called curl.m. okay, so you've got access to that in the resources section, so you can just have a wee play about with that. So if I was to run that, then it asks me for the curl, the I component of the vector field. So in this case the I component of the vector field is going to be given by minus y, and it asks me for the j component, which is going to be given by x. It also asks for a z component, so we just put in 0 for the z component, and this should draw out our fields. Okay, so that's just exactly what we've seen. Okay, and you can just move these round about to suit. Okay, so that's the first one. We'll go and have a little look, and the second part of this, the first one there, we'll see just now. Okay, so now if we were to change that vector field just slightly, so now the vector field is going to be equal to plus y minus j, and the k would be 0. Now the field would be rotating in the clockwise direction, and it means that the paddle there would be rotating in a clockwise direction. So as such, if it's rotating in a clockwise direction by the right hand rule, the value of the vector, the curl, would be in the k direction, and it would be a value of minus 2. Okay, so that's a value of minus 2. That's exactly what we see here. Okay, so let's move on to example number 2. So this example here is given by a vector field which is 0 in the I direction, and it's going to be e to the minus y squared in the j direction and 0 in the k direction. So it's slightly different from the one that we looked at. We've simplified it a little bit. So in this instance here, you can see that the variation is in the y direction, but if the paddle's sitting in here, then we've got an equal amount of force on this side of the paddle here as we have on that side of the paddle. So the paddle won't move, it won't rotate, and the curl will be equal to 0. Okay, and we can see up here the curl indeed is given by 0. Now in the final one, we're looking at a vector field which has a j component, and it's e to the minus x squared. So I've drawn out 3 different positions here. So the paddle here, there's a paddle sitting in the centre, there's a paddle slightly to the left, and a paddle slightly to the right. So you can see the paddle in the centre. We're going to have an equal amount of force on each of the paddles in the left and the right. So it means that the curl in this paddle is going to be equal to 0. And indeed, all along the central line here, the value here is in fact 0 for the curl. Now, in this example here, the paddle slightly shifted to the left. So in that case, that this right part of the paddle is going to have a greater force than the left, and it will turn in this anti-clockwise direction, which will give us a positive curl. And you can see here, example, at that point there, the curl is indeed positive. And the final one, the paddle shifted slightly to the right, so it means that there's going to be more force on the left hand paddle than the right, so it will travel in a clockwise direction. So that will ensure that the curl that we get will be a negative value for the curl. Okay, so just as a reminder, then the curl is in fact going to be a vector function, but we've not drawn it as a vector function here. We've just drawn it out as just some scalar. Okay, just to show the examples. Okay, so we've got the value here for our 2 equations. So our original equation here is e to the minus x squared, and the curl is going to be minus 2x e to the minus x squared, and that is worked out for us as well in that little bit of script that I've written. Okay, so finally, just a couple of points here on the curl. Remember, curl is a vector, so in this instance here, each point in space, if it was a 3-dimensional flow, would have a curl associated with it. So the curl would be, the direction of the arrow here for the curl would be determined by the right hand rule, and it would sit normal to the little surface, and the rotation would be given by the right hand rule. And I've drawn each of these out, so 3 different examples. Another thing to note as well is that in this instance here, if we have a ball and we've painted one side blue and left the other side black, now if the ball's rotating round in a vector field in an anti-clockwise direction, but if the actual axis of this ball here remains fixed and the ball doesn't rotate around its own axis, so at each position it's still sitting in the same position in the axis as it goes round, then in effect this here won't have any curl because it's not rotating on its own axis. So there are some aspects of curl that can be a little bit confusing. Okay, so I'll show you the code in Matlab, and that will allow us to finish off here. So here is the Matlab code. The function's called curl. It requests 3 inputs from the user, an I, a j and a k component, and it puts these into variables x in, y in and z in. It takes these components, which are a symbolic representation of the function of the field, and then it creates an actual mesh grid on x and y according to this mesh grid here, and it then plots out the quiver plot for it, and all the rest of this here is just to get it into a nice looking format. Okay, and then the second plot here is finding the the second part here this helps us to find the curl. So it's just a simple function here, MATLAB function called curl, which generates the curl, and we put the values for the curl in a variable called CUR. We then use the fsurf command in order to plot out that curl, and again the rest of this here is just in order to make the figure look nice and just the way I want it. Okay, so that's all there is to this. I hope that was of use to you. I would suggest that what you want to do is to go in and use the code in order to generate some vector fields of your own and check and see your understanding of curl. Okay, so thank you and goodbye.
In this video we're going to start looking at the gradient of a function. So this is sometimes written as grad f. So let's imagine we had a simple function of one variable x. So we've got a y-axis or x-axis and say y is a function of x. So we can then say that if we were to take a point on that graph and we were to look at the gradient at that point, then the gradient is shown in blue, and we can see that if we were to take a distance dx and then we come up to hit that gradient again at dy, then we can say that the rate of change of the function can be written as f derivative at x naught, and that's equal to our dy by dx. Now we can then take our dx up to this side here, so we'll be left with our dy equals f derivative of x naught times dx. Okay, so we're really just saying that if we go to that point there and we find the gradient at that point, which is f derived at x naught, and multiply by that delta x with that small height delta y. But remember, we're dealing with infinitesimals here, so dx in fact is an infinitesimal distance, so dy with an infinitesimal height as well. So we could write that out in vector format. We could say that we could find the rate of change of the function at x0, and that would be in the I direction, times our dx would equal our dy. Now we can do the same for a function of two variables. If we had z as a function of x and y, so there's our x, our y, and our z, then we can look at the derivative of the function with respect to x and of a two-dimensional function of two variables x naught, y naught in the direction of I, and we can look at the rate of change of the function as well in the y direction. So that's going to give us in effect a vector, one for a component in the I direction and a component in the j direction. That's going to equal our total differential, which is just the height dz. But of course, in these instances we have to use partial derivatives because if we differentiate with respect to x, we've got to hold y constant. When differentiate with respect to y, we've got to hold x constant. So let's have a little look at how this works. Now we're not going to go over it in terms of the vector, we'll just go over it in terms of a simple total derivative. So if we have z equals x cubed y plus xy squared, and we said what is the total derivative of dz, then what we do is we differentiate the function there, f, with respect to x, so we get 3x squared y plus y squared. We differentiate the function with respect to y, so we get x cubed plus 2xy, and then we multiply each of these by dx and dy respectively. So that there will give us our total differential dz. But now, what we're actually interested in is looking at it in terms of a vector quantity. So from this we can find a useful vector quantity, that is the rate of change of a function with respect to x in the I direction, and the rate of change of a function with respect to y in the j direction. So we've just rewritten that out in the next page. So we're looking at the partial f by partial x in the I direction plus partial f by partial y in the j direction. But we know that partial by partial xi plus partial by partial yj, well that can be written in terms of a shorthand form as the del operator. So that's equivalent to us just writing del times f. Okay, so this component here, del f equals partial f by partial x in the I plus partial f by partial y in the j. That there is just the gradient vector, or grad f. Now an interesting thing about this is that it turns a scalar function into a vector function. So let's say, for example, we're looking at the temperature at any point in our room, then this is just a scalar function. But then if we were to then find the gradient of that field, that scalar field, then we'd be looking at the rate of change of the temperature. So the rate of change of the temperature will have a direction and it'll have a magnitude. So this will now become a vector field. So that's important for what's going to follow in some of the videos coming up next. So again, best seen by example. So if we had z as a function of x and y, such as e equals x squared y plus xy cubed, if we were asked to find the gradient of that vector field at point 1, minus 2, then we differentiate that with respect to x, differentiate it with respect to y, and I'll leave you to have a look at the differentiation. And then we put the values of 1 minus 2 in for each of these, and we'll get the values of minus 12 and 13. So we're left with the gradient of the vector field at 1 minus 2 equals minus 12i plus 13j. So it tells us that the gradient of that scalar field at 1 minus 2 equals minus 12 in the I direction. So it changes at a rate of minus 12 in the I direction, and it changes at a rate of plus 13 in the j direction. Okay, so that's all there is here for the first part. Now the next part we're going to go and we'll look at something called the directional derivative. Okay, so thanks for listening, and I'll get you on the next video. In this video we're going to look at the idea of a directional derivative. So we've got a coordinate axis drawn out here. Here's our z, our x and our y, and we've got some surface here, z is a function of x and y, and we've got a point here on that surface, and if we were to drop that perpendicular down, we'd have the point on this xy plane, which would be x0, y0. So what we're going to ask is, what is the rate of change of the function, not with respect to the x direction or y direction, but with respect to some arbitrary direction. So the arbitrary direction is given by this vector here, so that's a vector u. So we're looking for the rate of change of this function in that direction. So the answer to that is the directional derivative, which we're going to introduce now. So it's a kind of wordy description here, which I think is quite reasonable. So we can take the magnitude of vector u to be equal to 1. So if we make the magnitude of vector u equal 1, because all we're really interested in vector u is at the directional component. But we have to ensure also that the scale of that vector u there is the same as the scale is on the axis for our x and y. Okay. So what we can do is we can split that vector u into its two components. That vector u will be a vector with a scalar component of ux in the I direction and a scalar component uy in the j direction. So you can see this here is going to be split into an x component and a y component. Now if we consider the idea, imagine that the actual vector u didn't have any j component whatsoever. Okay, so if vector u had no j component, so the j is in this direction here. Okay, so that's our j and that's our I. So if it had no j component whatsoever, then the only component it would have would be the I component. So it would mean that all of the rate of change of the function then would be associated with our partial f by partial x. Okay. Now, if we had the other way around about, if we had u had no I component, then all of the rate of change would be given by the factor of partial f by partial y in the j direction. But if we had u and it had both components in the I direction and the j direction, then the overall rate of change in that direction would be some proportion of the partial f by partial x in the I, and some proportion of the partial f by partial y in the j. So the next question is that what will the proportions be? Well, that was the reason for ensuring that the value of our u is in the same scale as the coordinate axis. So if the value of u is the same scale as the coordinate axis, it means that the component sections here, the ux and uy, are in the correct scales such that they provide the correct proportion of the rate of change in the x direction and the rate of change in the y direction. Okay, so it means that we can write that the partial f by partial x in the I direction times u of x, which is in the I direction, plus partial f by partial y in the j direction times your u of x and the u of y, that should actually say, shouldn't it? So that should be u of y in the j direction is going to equal our derivative here, which is the rate of change of our function at the point A in the direction of u. So what we can do is we can rewrite this out here using our dot product. So we can say and our del operator as well. So we can say partial by partial x in the I plus partial by partial y in the j times our value of f, and then we can dot that with our u. That's going to give us our del f dot u. So this thing here is the directional derivative. So the directional derivative is the derivative at point A of a function f in the direction of u, and it's given by del f dotted with our vector u. Okay, now these are best understood by examples. So here's a little example here. If we say if a function of x and y equals x squared plus 3x y squared, then we're asked to find the directional derivative at point 1, 2 in the direction, say, towards the origin. So the direction towards the origin is just going to be equal, well, we've got to come along -1 and down -2 to get to the origin. So it's going to be -1 in the I direction, -2 in the j direction. So what we have to do first of all is work out that in terms of a unit vector. So we've got to make u the unit vector. So in order to do that, we take the vector and we divide it by the magnitude of the vector, which is just going to be our -1 squared plus -2 squared root, which is going to be the root of 5. Okay, so this thing here is going to give us the magnitude of our going to give us our vector in terms of a unit magnitude. So we'll finish this off here. So now we're looking at the partial f by partial x at point 1 and 2. So that's the partial f by partial x at point 1 and 2 gives us 14. Partial f by partial y at point 1, 2 gives us 6xy, and that gives a value of 12. So now we work out our derivative. Okay, so our del f, which is the gradient vector, is going to equal our 14i plus 12j. So we've seen that gradient vector from the previous video. So now what we do, we take the gradient vector and we dot it with our directional vector u. So that's going to give us our 14i plus 12j dotted with our -1 upon root 5i minus 2 upon root 5j. Okay, so whenever you can see now, when we multiply these out, you can see these for doing the dot product, is that the i's would multiply by the I to give us a 1, the I would multiply by the j, which gives us a 0, and the j term would multiply by the j to give us a value, but the j term when multiplied by the I, that would just give us a value of 0. So what we're going to be left with is the I times I is 1, so it's going to be our 14 upon root 5, minus 14 upon root 5, sorry, and minus 24 upon root 5 equals minus 38 upon root 5. So that's just a scalar quantity. So that's going to give us our final value for our rate of change of the function at point A in the direction of u. And you can see that it's kind of a bit of common sense. This is the rate of change of the function in the I direction, the rate of change of the function in the j direction, and this gives you the proportion of this rate of change in the I direction for your unit vector u, and this gives us the proportion of this value here in the direction of the j direction for that vector u as well. Okay, so one more thing that's interesting here, we're interested in the magnitude and the direction here of our gradient vector del f. Okay, so if we were to look at our directional derivative, so that's the gradient of the function f at point A in the direction u is going to be equal to our del f of a dot u, but that can be rewritten in vector notation and as the dot product as the magnitude of a times the magnitude of b cos of theta. So in this case, magnitude of a vector a, the first vector is going to be our del f of a, so it's the magnitude of this times the magnitude of that times the cos of the angle between, but we know the magnitude of u is equal to 1 because we've worked it out and defined it that way. So we're just left with this directional derivative equals this del f of a and the magnitude of it times the cos of the angle theta. So we know that when theta equals 0, then the cos of theta is a maximum value of 1. Okay, so it means that this direction here, the value del f of a, that is the gradient, but it's the actual maximum gradient at a point. Okay, so when we find the gradient vector at a point, it actually gives us the direction of the maximum rate of change at that point, and also the magnitude of this gradient vector gives us the actual magnitude of the rate of change as well. Okay, so that's an important point. So that's all there is to this section. Next video we'll go and we'll look at some ideas in equipotential surfaces which are related here to the gradient vector. Okay, so thank you for listening and goodbye. In this video we're going to look at the idea of an equipotential surface. So if we consider a surface, say a constant temperature in a room, so you heat a room up but there's a certain surface there in that room where the temperature has remained constant. Okay, so we'll draw that surface out here. So this is the surface T equals T naught. Okay, so the temperature here at this surface in the room is kept at a constant temperature T naught. Okay, now if we were to take a vector u, which is going to be our tangent to the surface at that point, then we're able to say that the rate of change of this, the temperature with respect to some distance along this vector u, say the distance ds, is going to be equal to 0 because there is no rate of change of the function, the temperature T along that surface, because it's defined as being kept constant. Okay, so if it's kept constant, the rate of change has to be 0. So it means that if that u is a tangent to the surface, then we can say that the rate of change of that temperature with respect to a displacement along the surface ds, as we've said, is equal to 0. But that's then, according to what we've looked at in terms of the directional derivative, we can say that we take the vector u and we dot it with our delta t, which this here will give us our directional derivative. It also will be equal to a value of 0. But it means that these two vectors here, u and del t are going to equal 0. So in order for both the vectors after the dot product equal to 0, then both vectors must be perpendicular. Okay, so in general, delta f is going to be normal to a scalar surface when that surface is defined as a constant, so a function x, y, z is a constant. Okay, so again, best understood by a simple example. If we had a sphere, so sphere is given by our equation x squared plus y squared plus z squared would equal some constants, where the constant would be the radius. Then our del f, well, del f then is going to be given by, we're going to differentiate with respect to x, y and z, so that's going to give us our 2ix plus jy plus kz equals 2r. Now the del f is the gradient vector, so we've seen from the previous video that gives us the direction of the maximum rate of change, and we can see here that the direction of maximum rate of change is in the direction of the radius. So that's as we would expect. As we move away from our sphere in the direction of the radius, then that's going to be the direction of the greatest rate of change, and that's going to be sitting at perpendicular to the equipotential surfaces, which are the spheres of constant radius r. Okay, so we could also look and see that we would have a zero rate of change if we were to follow the equipotential surfaces round about the sphere. Okay, so if we're actually to go along the surface of a sphere, then we wouldn't have any rate of change of the function in that direction. Okay, so that's all there is for this video, and I'll get you on the next video. Okay, goodbye.
In this video we're going to look at the gradient in cylindrical coordinates. Now we're going to do it in a slightly different method than what we've seen whenever we looked at the cylindrical coordinates for the divergence and curl. So we've got our z, our x and our y axis drawn here, and we have our typical cylindrical coordinates. So we've got a delta r here, and we have our r delta theta, assuming that the angle theta is in radians, and we have a value of delta z. Now we can look at the distance here as well between this point here up to the top point here at delta z. We call that distance there delta s. Now when we look at the total differential of the function, then we're looking at the partial f by partial r, so the rate of change of the function with respect to r times the delta r, and the rate of change of the function with respect to theta times delta theta, and the rate of change of the function z with respect to delta z. So we're taking that as a first order approximation there to the change in the function delta f. Now what we can do is we can look at delta f in terms of that delta s, so that's that distance there. So delta s then will become a vector, and we're going to come along the distance delta r, and the component will be er, and that's a unit component of 1, and we'll come round the distance r delta theta, and that's the unit component e theta, and again delta z with the unit component ez. Now the next little trick here is we'll rewrite this delta f here in terms of this delta s. Okay, so whenever we do that, if you dot product this term here with the delta s, you're going to get back to our delta f term here. So if you were to multiply this here with this line here, you'll get back to our delta f, and you'll see we've got an extra factor here of 1 upon r in order to negate the factor of r here. So we're going to have our this section here time dotted with our delta s. Now what we're going to do is we're going to make this direction here, our delta s, that's going to become a unit vector. So we'll make that a unit vector u, And you can make it unit vector u by taking the vector delta s and dividing it by the magnitude of that vector delta s. Okay, so that's what the delta, the u term would become of length 1. And then we take the limit as delta s tends to 0 over partial or delta f by delta s, so we get our df by ds. And when we do that, you can see that this value here for our delta s comes down, and we're only going to be left with our factor. So this factor here, delta s, comes down, and we're only going to be left with our factor of u. Okay, so it's going to be dotted with our value of u. So we take this limit, we're going to be left with our partial f by partial r plus our partial f by partial theta and partial f by partial z, and it's going to be in the direction of our er, e theta and ez, and there should be actually a 1 upon r in there as well, so I'll just pop that in there. So that should say 1 upon r, and that's our e theta. Now what we have inside the brackets here is nothing other than the gradient. So this here is the gradient in the cylindrical coordinates. So partial f by partial r in the direction of r, 1 upon r partial f by partial theta in the direction of theta, partial f by partial z in the direction of z. So that's all there is for this video. In the next video we'll use the same process in order to work out the gradient in spherical coordinates. Okay, goodbye.
In this video we're going to look at the gradient in spherical coordinates. So similar process that we've seen in the previous video when we looked at it in terms of a cylindrical coordinate system. So we've got our coordinate axes are z, x and our y, and the spherical one is going to be very similar to the cylindrical one. We're going to have a distance delta r, we're going to have a distance round here which is going to be our r delta theta, assuming theta is in radians. In cylindrical coordinates we would just go up a distance z, but now we're going to cut in around the arc of a sphere to get to this point here. So we're going to be cutting around that distance. It's going to be given by r delta phi sine theta. Now if you're unsure where that comes from, you can have a look at the previous videos when we looked at the spherical coordinate systems for divergence and also for curl. So the distance here, delta s, which is a vector, is going to be given by the path delta r and the path r delta theta and the path r delta phi sine theta. So we can say our delta s is equal to our delta r in the er direction, delta r delta theta in the e theta direction, and sine theta times r delta theta in the r delta phi, in the e phi direction. Now we also didn't see in the previous video that we want to make sure that if we were to call this distance here our vector, and we'll just call it our vector u, we want to make sure that the vector u has been normalized to 1. Okay, so we do that by dividing the delta s by the magnitude of the delta s. Okay, so it means that we can then write the function then as delta f as partial f by partial r in the r direction, and it's going to be 1 upon r, to get rid of this r up here, partial f by partial theta in the e theta direction, and also in the phi direction we're going to get rid of the r sine theta, so it's going to be 1 upon r sine theta e phi partial f by partial phi, and that would be dotted with our delta s. Okay, so it means then that if we were to take the limit as the delta s tends to 0 over our delta f by delta s, we get our df by ds, which is equal to the thing here in the brackets, dotted with our normalised vector u. So the thing inside the brackets is nothing other than the thing we've been looking for from the beginning, which is the gradient in spherical coordinates. So that's all there is to this video. I'll get you on the next video. Okay, goodbye.
In this video we're going to show you how to do 3D plots that will show you the gradient of a scalar field. So we've got a few here already done. So I've taken a scalar function here of just two variables x and y. So f is a function of x and y such that it equals cos xy. So that's the cos xy surface there. And on the right hand side we've taken the gradient of that, so we've found the del f. So you can see here that the gradient here, the little blue arrows represent the length of the blue arrows represent the actual gradient of the point, and the direction represents the direction of steepest ascent. And you can see here that the steepest section of this curve here is going to be coming up through this route there, and up through there, and up along there. And you can see that the arrows are all going to be pointing in the direction towards the top. And at the actual top surface along this line here, and along that axis, the gradient is actually 0, so it means that the arrows are small along these directions. But I've also put in the equipotentials there. So there's a few other ones I've done, and you can quickly have a little look at those. Okay, so now we're going to get into Matlab and we'll show you how to generate those. Okay, so this is the script I've used here, and I'll show you it working first, and then I'll go and read through the script for you. So you've got access to this function here called the Matlab function called gradient.m, so it should be in the resources section. So if you've got access to Matlab, you can just run that. It says enter a 2D function, so you can just put in whatever 2D function you want. So we'll just do the first one that we've seen in the last page, which is the cos of x times y. Okay, when we press return it should generate those functions. Okay, so there you go, that's generated both those functions. So on the left hand side is the cos xy function, and on the right hand side we've got the gradient of that cos xy function, which is this function here. And again, you can adjust the angle of that so it looks the same as the previous one we looked at, and you can adjust the angle of that as well. So you can see that these two here are just the same as what we have generated in the previous page. Okay, so those are the same as those here. Okay, so it means you can go ahead and you can generate all the rest of these functions, and you can generate which other functions you happen to want to put in. So it only does it for 2D functions because it just shows up the gradient. It's much simpler to see. Okay, so let's have a look at the actual Matlab function, and we'll get in and see roughly how it works. So we've got a function called gradient. It prompts the user to input the actual value of the function. It saves that value of the function in a variable called f, and then it plots out the actual function there using the f surf, and the limits are -2 to 2, -2 to 2, and there's just a few labels here, and that adds the actual function into the figure. Okay, then you can generate the gradient of the function using the gradient. Okay, so that's the Matlab gradient function there, and then it goes on to figure 2. In figure 2 we generate a quiver plot. So it takes this symbolic function that we've put in, and it generates actual x and y components in a matrix for that particular function. and then plots it there using the quiver plot, and also add in a contour plot as well. Okay, and that's really all there is to it, and there's a few labels there as well. Okay, so not a lot to it, so you can get in and have a wee play with that yourself, and it's actually quite fun, and you're able to generate some pretty cool functions. Okay, so thank you for listening to this. I hope the little tool's of use. I would suggest you go out and have a go at it, because it really does help you understand some of the concepts. So thank you and goodbye.
In this video we're going to look at the last operator that we're going to be working on. So this is called the Laplacian. Now if we think back to our original question, which was how do we find an electrostatic field given some random charge distribution? Now the path that we followed was that we worked out the differential form of Gauss's law, which can be written as the divergence of the electric field is going to equal to the charge density divided by epsilon naught. Okay, so we derived that one a while ago. Now this here has got it's one equation and three unknowns, so Ex, Ey and Ez, so we're still not easily going to be able to solve it. But now we've got an extra piece of information, because we know that the electric field is conservative. That is that the line integral here of this tangential component of the electric field is going to be path independent. So it means then that from what we've seen in the previous videos that we can associate some scalar function phi of x, y and z to that electric field. So then we're able to see that from the previous video that electric field is going to equal to the del phi. Okay, so it's going to be the rate of change of this function, scalar function phi. Now there's actually a negative sign put in there, and the negative sign is just ensures that the positive charges actually are going to move downhill with the decreasing level of potentials. Okay, so it's just really to make all of the all the sums come out right in the right sense. Okay, so you don't worry too much about that. Okay, so we have the electric field is equal to, written as minus grad phi, which is minus this grad phi here. Okay, so from 1 and 2, these two equations, equation 1 there and that equation 2, now we can put equation 2 into equation 1. Okay, so we can replace this electric field here with minus grad phi. Okay, so then we're going to end up with our del dot, and it's going to be minus grad phi equals the rho upon epsilon naught. So it means that we can take out the negative sign here, and we'll now replace the negative sign in the minus rho upon epsilon naught. So what is this Laplacian? What does it look like? Well, if we were to take this operator there, the del dot del phi, that's going to be equal to I d by dx plus I d by dy plus k d by dz, and it's going to be dotted with the I d phi by dx, I d phi by dy, k d phi by dz. Okay, so that's going to equal del squared phi by dx squared and del squared phi by partial y squared and partial squared phi by partial z squared equals minus rho upon epsilon naught. Okay, so that looks then like the second differential of that scalar function. So in an analogous sense, in a single variable function, the second differential would give us the rate of change of the gradient or the curvature. So we can think about this as the form of a curvature of that scalar field. So it means that this operator here, as we've seen, it can be written and it's called the Laplacian. It just can be written, the actual operator itself can be written as partial squared by partial x squared, partial squared by partial y squared, plus partial squared by partial z squared equals this del squared. Okay, and this thing here is the actual thing called the Laplacian. So that's the operator that we've been interested in looking at. So again, we can write that as del squared equals, it's actually the divergence of the gradient. Because if you've got a function del squared f, it would be del dot del f, which is equal to the divergence of, well, that del f is just the gradient of the function f. Now, in the electrostatics case, the del squared phi is going to equal minus rho upon epsilon naught. Now that's called Poisson's equation. Okay, and it's a one equation and one unknown. The unknown is the scalar function x, y, and z. So, if we had a problem finding the electrostatic field given a random charge distribution, what we could do is we could find the scalar function phi of x, y, z, and then from that we can get the electric field by taking the minus del phi of that. Now, where there is no electric charge, then the actual charge density rho equals 0. So in that case, the Poisson's equation simplifies to del squared phi equals 0, which is called Laplace's equation. Okay, so that's just a brief cursory introduction to the idea of the Laplacian. Okay, so thank you for listening, and goodbye.
In this video we're going to look at a couple of examples of using Laplace's equations in order to find the potential and then the electrostatic field. So these are simple geometrically simple examples, so just to give you a taster or a feel for it. So let's first consider two parallel plates which are separated by a distance s. One of the plates is held at a potential, so that psi is equal to the potential, so that's potential equals 0 in this plate, and the potential psi in that plate equals a value v0. Now the plates are considered to be infinitely large, so it means that in the z and in the y direction they're just infinite large plates, so the only variation of electric field in this example will be in the x direction along this path s. So the question then is, what is the potential inside here, and what is the electric field in the region between the two plates? So if we were to write down the Laplace equation, so we've got our del squared psi equals 0, then we've seen from above, from just the simple geometry of the system, that the only variation is in the x direction. So it means that the d squared psi by dz and d squared psi by dy are going to equal 0. So you're only going to be left with one of the factors here. And the boundary conditions for this little differential equation here are that psi equals 0 at x equals 0, and it's v naught at x equals s. So it's just these boundary conditions here, psi equals 0 here, and psi equals v naught at a distance s. So there's standard solution for that differential equation there. It's going to be the form of psi. Now I've actually written that out, written it out properly. It should be psi. So psi is going to equal v naught x upon s. Now you can see that there, because if you differentiate this twice, you should get back to a 0. So we differentiate that once with respect to x. Well, v naught and s are just fixed constants, so they just look like constants. So you're just left with your constant here. When you differentiate a constant gain, you get 0. Okay, so that's a simple little differential equation there to solve. So now we've found the potential, and we can find the electric field by finding the negative of the gradient of that potential. So again, all we're doing is just differentiating the potential once, and we're only interested in it in the I direction, because the y and the z have disappeared, so there's no j and there's no k. So it's just, in effect, we just went through the first part here, we've just differentiated this once, and we've got the v naught upon s. So we'll work through the differentiation. So we're differentiating that. The electric field is minus partial y partial x of this v naught x upon s, and as I said, the v naught and s are constants, so the only variations in x, so it's just like a constant, just like saying differentiate 5x. So you're just left with a value of 5 at the end, which is the v naught upon s. So you've got the electric field there is v naught upon s. So really what it's saying is that, and that's obviously it's in the x direction, so the electric field is a vector and it's normal to the plates, and the magnitude is going to be directly proportional to the value of the voltage, the value of the potential of v naught on one of the right hand plate, and it's also going to be inversely proportional to the distance from the plate S. Okay, so that really acts, and we've seen that, or you may have seen that as the starting point for analysing a parallel plate capacitor. Okay, so example number 2. We have a sphere here in pink, and inside it is another sphere in blue. The radius of sphere in the blue is r1. The radius of the pink sphere is r2. The internal sphere is kept at a potential v naught, and the outer sphere is kept at a potential equal to 0. And we're asking, what is the field, what is the potential in the area between, and what is the field in the area between. Now, what we do is we would use polar coordinates for this, but we notice that the only variation of this is going to be with respect to r, okay, because of the symmetry of the system. So it means that there's no variation with respect to theta, and there's no variation with respect to phi. So it's only going to leave us with one part of the spherical coordinate, this is the spherical value for this. So it's only going to leave us with the 1 upon r squared d by dr, r squared d psi by dr, and that's going to be equal to 0. Okay. Now we went through the derivation of the spherical coordinates, so you'll see that as part of the one of the previous videos. Okay, so if we look at the boundary conditions, we know that psi of r equals v naught whenever r equals r1, and it equals 0 when r equals r2. So that's just the value of the potentials on the spheres at radius r1 and r2. So r1 is the blue sphere in the centre, and r2 is the pink sphere on the outside. Okay, the blue sphere and the pink sphere. So again, it's just a little differential equation. So what we can do, because they're equal to 0 there, we can multiply throughout by r. So this side by r and that side by r. Okay, it's just the r squares is going to disappear, and we can replace the d psi by dr with a value of phi. Okay, so this whole thing you just replace with a value of phi. So this simplifies then to d by dr of r times phi equals 0. So whenever you differentiate something and it ends up 0, then that something there must be a constant. Okay, So it means that this r squared phi, that must be a constant, so we'll call that constant C1. So we know that phi, which is d psi by dr, is going to be a constant. It's going to be the C1 divided by the R2. Okay, so just transpose that for the phi. Okay, so it means that we can then say that if we want to find that value of the potential, it's just going to integrate this to get this section here to get the psi. So that's just going to be the integral of C1 upon R2. So that's just going to give us minus C1 upon R plus a constant of integration C2. So this is a little equation here that we've been looking for. And the boundary conditions for that differential equation are going to be given by minus C1 upon R1 plus C2 equals V0, and minus C1 upon R2 plus C2 equals 0. Okay, so all I've done is put the boundary conditions into this little equation. Okay, so whenever we transpose these boundary conditions here, so we're just making C1 the subject of this formula, and we're making C2 the subject of this formula, so I should say 2. Just change that. So that should say C2. There we go. C2 is the subject of that formula. Okay, so we've just transposed these. I've not put in all the algebra, so if you just transpose these, you'll get this one and you'll get that one. And then you can stick the boundary conditions here back into our formula here, and we'll get our psi with respect to r equals this here. Okay, so that's us found the first part of it. We're looking for the potential. Now we want to go ahead and we want to find the actual field. So we can find the field by define it as the minus the gradient of the potential. So all we do is we just differentiate that last equation. So we just differentiate that last equation with respect to r. Now these are all constants, so this first term would just disappear. Now whenever you multiply that with this, you get the V0 R1, and then the R2 is a constant as well, all upon R1 minus R2. So the only thing that you're actually differentiating is the 1 upon R. Okay, so whenever you differentiate the 1 upon R, you get your 1 upon R squared. Okay, so this here is the electric field, and of course it's only defined with respect to the R as your variable. Okay, so these are only two of the simple solutions to second order partial differential equations. Now this is a huge and rich field, and we've only scratched the surface of it, but a lot of the solutions as well are going to be done on the computers, okay, as a part of computer simulations of partial differential equations. And the examples we looked at there, they're geometrically simple, so it makes the calculations a lot simpler for us. But it was just to give you an indication of how we're going to go and actually use the Laplacian. So that's all it is for this video. Thank you for listening, and goodbye. We're going to look at one example of the Laplacian in Matlab. Now I've created an M file called Laplacian.m, and that's available to you in the resources section of this video. So I've written out the Laplacian in this form here, and we've seen it before. It's the divergence of the gradient. So let's have a little look at this process. Now what we're going to do is we're going to stick a function in, so it's going to be a two-dimensional function. In this instance here, the example we're using is the function x times e to the minus x squared minus y squared. and we've plotted out that function here, and you can see makes a rise here, and there's a dip here, and it drops down the same kind of distance here. Okay, and then you see just the zero plane there. Now what we've done is we'll take that function and we've found the gradient of that function. So the gradient of that function, you can see that the yellow section here corresponds to the yellow section here. So the gradient is going to give us the direction of the steepest ascent. So you can see all of the arrows are pointing inwards because the steepest ascent here is going to be up towards this point here, and this end here all the arrows are pointing outwards, okay, because the steepest ascent is going to be up towards this point here, or if you're in this hole in here, it's going to be up in this direction. And you can see the equipotentials there as well. So we know that whenever we work out the divergence of this point here, because all of the arrows are pointing in towards it and they tend towards the point here, at the point at the top there won't be any arrow because the gradient will be 0. So we can see here that this is going to be a sink, and we can see this point here is going to be a source. So we know whenever we generate the divergence that the sink is going to have a negative value for divergence and the source is going to have a positive value for divergence. And I've worked out the divergence of this function here. So this is the divergence here. So the negative values here are for the sink and the positive values here are for the source. So in effect this divergence of the gradient, well, this here is the Laplacian. So we've taken a scalar function, produced a vector, and from that vector function we produced another scalar. Now you can see the actual values of the gradient, that's the function that's been worked out. Now it's been cut off the end slightly just to fit it in, but that's the equation there for the gradient, and there's an equation there for the divergence of that gradient. And you can see then that the Laplacian is really looks like a second derivative of this function, and it's analogous to the second derivative of a normal function of just one variable. So if you had a function of one variable, then you could work out the rate of change at this point is 0, the rate of change at that point is 0, but if you took the second derivative, then the second derivative of that function is going to be for a local minimum, the second derivative is going to be greater than 0, and for a local maximum the second derivative is going to be less than 0. And that's really what we're seeing here. We're seeing it for a vector function. So the Laplacian has gives us that second derivative. Okay, so it's the divergence of the function here, the vector function. Now we mentioned before that in electrostatics we're interested in working out whether a function can have can be an electrostatic field, and we answered that by saying, well, if the curl is equal to 0, then we can ensure that that has an electrostatic field. Now in this instance here, and if that is the case, then we can associate with a vector field the scalar function, which is this function here associated with this vector field here. Now we know that in this instance here we've started off with a scalar function, and then we've generated we've generated a vector field. Okay, so we can be sure then, because we've done it in this process, whenever we find out the curl of this field, we should get a value of 0. And whenever we put this field here into the curl equation, the curl program, so there's another program there that we've used before, but I'll put it down in the resource section, which allows us to generate the curl of a vector field. So if we put this vector field here into that curl equation, we will get 0, and that's exactly what we've got here. Okay, so what I can do is I can show you this working in Matlab. So let's just bring Matlab up. So this is the function called Laplacian. I've also got a function up called curl. Okay, so we'll start off with Laplacian, and I've already created these functions, so it saves me typing in. So what we'll do is we'll run the Laplacian, and it asks for a 2D function. Okay, so the 2D function that we're going to put in is just the one that we've just been looking at. So it's going to be x times exp, and we're going to have minus x hat 2 minus y hat 2. Okay, so this is going to produce our 3 curves, which we've just seen. So we'll try and squeeze these in so you can see them. So we have our original function, which we've just drawn out. So that's our 2-dimensional function we just created, and we're going to have our scalar, our vector function here as well. So that's our vector field, which has been generated from finding the gradient of this. And finally, we're going to work out the divergence of that gradient, which gives us the Laplacian, and that's the divergence of the gradient there. So they're just turned round, and what's the y-axis there. So you can just adjust these round to get the axes in the same order. Okay, so what you could do is you can take that little bit of code, and then you could work out what the gradient is. So we've got the gradient field here. So if we were to put this gradient field into the curl program, then we should get a curl of 0. So let's just put that in. Now, see, I've got it up here, so it's looking for the I component. So that's the I component there, and then it's looking for the j component. That's the j component there, and the z component 0. So whenever we work this out, we should get 0 for our curl, and it's drawn out that vector field, which is just the same vector field we've seen in the previous page, and that there is given as the, I'll show it right in here. Okay, so that's the vector field that we've created, and it's shown that the vector field here, the curl of that field, is indeed equal to 0, as we had hoped. Now a quick run through the Laplacian code here. Similar to the rest of them, we ask for an input, and we stick the input function in f. We then draw out that function there using the f surf. So that's the figure 1. We find the gradient of it and put it into g, and we do a quiver plot of that gradient of the gradient g, which gives us our second function, our second plot, which is the vector field, and the rest of it is just adding on niceties to try and make it look nicer. And finally, we look at create the divergence of that gradient, and then from that we produce the f surf of that divergence, which will gives us a further plot, figure number 3, and the rest of this is just the add-ons to make it look a bit nice and neat. So that's all there is to this. I suggest that you go ahead and have a little play with that and try and get it working, and it'll help you to understand a bit about the Laplacian. Okay, so thank you for listening, and goodbye. In this video, we're going to look at a summary of all the equations that we've derived through this course. So hopefully the next time you see these equations, you won't be as scared of them, and you'll know where they come from. So we looked at the divergence theorem, which relates the surface integral of a normal component of a field to the volume integral of a related component, which is the divergence of the field. Stoke's theorem looked at the tangential component of the field round a loop, which we call the circulation, and related that to a surface integral of a related quantity, and that related quantity is the normal component of the cross product of the field, or the curl of the field. We looked at divergence. We looked at divergence in Cartesian, cylindrical and spherical coordinates. We also looked at curl in Cartesian, cylindrical and spherical coordinates. We also looked at the gradient in Cartesian, cylindrical and spherical coordinates and the Laplacian in Cartesian, cylindrical and spherical coordinates. So we also looked at the question, we answered the question, how do we find the electric field given some charge distribution, and that was a theme that ran throughout all of the videos, and we introduced a few of the ideas about electromagnetics. So I hope this has been of use to you, and the most important thing is that you don't get scared by the equations because you know where they come from. Thank you for listening, and goodbye. So this is the end of the course. I hope you enjoyed the course. I hope it was of value to you. Hopefully you can now take what you've learned here and maybe go on and study some electromagnetics. It's a really fascinating subject, and a lot of the maths that you've learned so far in this video series, if you've covered it, will stand you in good stead to understand Maxwell's electromagnetics. So thank you for taking the course, and goodbye.